by Mohit Bansal, Raymond Mooney, and Chris Potts. So I'm Saptarshi Ghosh. I'm an assistant professor at IIT Kharagpur, and I'll be chairing this session. So once again, welcome everyone. So the first talk would be by Dr. Mohit Bansal. Is he online? Yes. Hi.
Yeah,
hi Mohit. Yeah.
And if it's too early, like I'm happy to wait a few minutes if you want. Like
yeah, maybe
it's very early.
So should we wait for a couple of minutes?
Yeah, I've kept the talk more towards like 25 to 30 minutes. So I think we have. I mean, I know it's very early, but
yeah, it's just 8 a.m. in India.
Options.
So yeah. So let's wait a couple of minutes. Let me introduce you, and then we can wait a couple of minutes and then start. Yeah. So Dr. Mohit Bansal is an associate professor and the director of the Merge Lab at the Computer Science Department at the University of North Carolina, Chapel Hill. Prior to this, he was a research assistant professor at TTI Chicago. He received his PhD from UC Berkeley in 2013. His research expertise is in statistical NLP and machine learning, with a particular focus on multimodal, grounded, and embodied semantics, human-like language generation, question answering, and interpretable and generalizable deep learning. He is a recipient of several prestigious awards, including the 2020 ICHKAI Early Career Spotlight, 2019 DARPA Directors Fellowship, 2019 Google Focused Research Award, 2019 Microsoft Investigator Fellowship, and the 2019 NSF Career Award. So it's great to have Mohit today here, and he would be talking on knowledgeable and spatial temporal vision plus language. So yeah, Mohit, so let us wait for a couple of minutes and then we can start. Hello. Okay, there seems to be some network issues. I'm audible to the others, right, Mayank?
Yes, you are audible. He got disconnected somehow.
Yeah, I think Mohit got disconnected. Fine, so he'll come back.
Yeah, hi. I think you're mute, Saptarshi.
Yeah, oh, hi Mohit. Yeah, okay.
Yeah, so, somehow my Zoom sort of crashed.
No, that's fine, sure.
But I didn't need to hear my own bio, so I guess that. Thanks. But thanks for introducing me. And should I start the talk now?
Yeah, I think you can start the talk now. It's 5 minutes past 8. So
let me share my screen. Okay, so if I do...
Yeah, I can see the screen. Right.
Okay. And can you see it moving?
Yes.
Okay.
I think you are good to go. Over to you.
Okay, great. Everyone, for joining the talk this early, especially the ones joining from India, which are probably most of the audience, and thanks for having me. as one of the speakers for this exciting event. Talking about knowledgeable and spatiotemporal vision and language. So the idea here is that there'll be two parts to the talk. One is the first part will be describing a series of video and language compositional kinds of reasoning tasks that we've built over the last few years as good evaluation benchmarks to be able to test the capabilities of the kinds of multimodal models we want, right? Because for that, we first need also good evaluation benchmarks that need both kinds of modalities and also not static images, but dynamic information in spatiotemporal videos, and also balanced across needing information from both the vision and language side. And then the second part of the talk, we'll probably keep shorter, or maybe half and half, would be how to start looking at different ways of building these large-scale pre-trained multimodal models from different perspectives, vision and language, or using vision to improve language-based models, or vice versa, or video plus language pre-trained, and so on. Moving towards the goal of maybe some unification and generalization and efficiency in such models. Okay, great. So the first part, like I said, will be video-based dynamic spatial temporal information and tasks for that. So like I said, the goal of the first part of the talk is that when we look at real-world applications around us, most of them need multiple modalities, right? Not just language or not just vision, but usually several things in a combined sort of information to get a complete reasoning, right, of this activity. So the same thing, if you're trying to build models that are multimodal in their capabilities, we need to have good evaluation benchmarks that can test these models' capabilities in performing compositional cross-modal reasoning. So that's why we will discuss specifically video and language-based benchmarks. I said, unlike images, videos are more realistic, and that's how we see the world as opposed to through static fixed images, where they do have dynamically moving information both spatially and temporally. And we look at different types of reasoning tasks here. So I'll give a few examples, answering tasks and also retrieval. And then the couple of last ones will be things like predicting what the more likely events are given a certain. And also the last part will be where you are trying to generate a summary of video, but also not just a uniform summary, but trying to learn the saliency of different parts of the video summary. And the piece will be a unified combining all these tasks and promoting multitask models. Okay. The first part is known as TVQA. So this was EMNLP 2018, where we tried to the largest video question answering datasets, expand different kinds of video genres or categories, and also covered both the video information and the language information in the conversation or the subtitles. And the most important part was that we tried to make this a compositional task where the question had to be answered by combining information from the video and the language in the subtitles or the conversation. And then I'll also discuss how to make it both not just temporally localized, but also spatially. So the example here would be that we would questions of the type, for example, what is Sheldon holding when he's talking to Howard about swords? So the idea here would be that when person X is talking about some objects, you first have to detect, the model will have to detect which part of the video, a long video, which clip would be talking about a specific thing. And then in that range of timestamps, you go and do more VQA style tasks like what was this other person named Sheldon holding? So this is one way of having compositional questions, but you could have all kinds of combinations. You could also have something like what was person X talking about when person Y entered the door. So first you have to figure out the timestamps of the video where person Y entered the door, and then you go and look at the dialogue and say what were they talking, what was the other person talking about at that in that time period. This was basically a data set that point around 21 or 22,000 video clips with almost 150,000 pairs of questions and answers. And the average length was around 76 seconds. It had question source coming both from text and video, and it had timestamps annotated. And then if you look at the top part of the slide, then it also covers kinds of genres. So would be things where you're talking about day-to-day activities, right? That happen around us. Whereas it also had medical and crime genres, which would be talking about very different kinds of events and activities. So this would be a simple way to have a resource like TV shows, but be able to capture all kinds of different genres of activities that the model needs. And the right side on the top shows different types that we were collecting. So it was not just things like what and when, but also things like how and why, right? So it's a whole spectrum of the types of reasonings needed in these questions. Extension of this called TVQA Plus in a later conference was more about not once you have figured out the timestamp, right, which contains the answer, you don't just do the temporal localization, but you also want the model to be able to do localization. So inside those timestamps, when you are saying what was person X holding, and the answer was a computer or a laptop, then the model also has to visualize and ground or localize the spatial bounding box or segmentation kind of information for you. So this has a good advantage where we sometimes multiple choice question answering datasets can have models take shortcuts. Maybe they will find the right answer, but more because there's not enough adversarial or tricky negative answers or distractors. So in this case, you are forcing the model to be more faithful and more interpretable, because it's also supposed to tell you the location of the answer, not just the name of the answer. Then the next category of tasks would be more on the retrieval side. So this is TVR, text plus video moment retrieval.
Hello, Mohit.
I think.
Okay, yeah, I think again some
The presentation has frozen.
Yeah, so again some network problems, I guess. So let's see. I mean, hopefully you'll be back.
Hello.
Hi,
Yeah,
Mohit.
Not sure what's going on. Like, this is the first time Zoom's crashing on me, maybe in the last 2-3 years. So did I end at the TVR part?
Yeah,
Yes.
you were at the TVR Plus.
Okay, great. So let me share again. Yeah, if it happens again, sorry in advance. I'll try to log in as quickly as possible. So Yeah, so basically, as I was saying, the difference between this task and the previous task is that here it's not a single clip, right? You're first having the model to decide which of the 10,000 or 100,000 videos does this query get answered in. And then inside that video, then you have to do the moment localization. So that's sort of like two tasks. BCMR is video corpus moment retrieval, where inside that corpus you find the right video, and then the SVMR, single video moment retrieval task, goes inside that retrieved video and localizes the moment. So again, TVR was one of the largest of its kind. So it had around, again, 22,000 videos, 110 queries. It had a very large vocabulary size. Also, the average question length was pretty reasonably large. Like average length of the moments per video. And then it had question context, like I said, coming both from the video and the text. It also had the question type annotated, and it had an individual query written by annotators as opposed to having a span from an existing paragraph being treated as a span-based query. It was independently written novel queries. It also had this nice property where the distribution of moments, if you look at it on the left side, the moments were relatively shorter, so more challenging to find, while the queries were relatively longer and hence more challenging to understand. And the last property that was useful is that on average, the number of actions and number of people involved in these queries was greater than equal to 2, as opposed to usually having only one action or one person involved. In terms of models for this task, we had an initial XML backbone here, which was a good starting point for future models. And the basic idea here was that you would first compute all the quick query and clip similarities, right, for each clip and the given query. And then you would basically run a convolutional start-end kind of edge detector idea to be able to predict, like, given this query clip similarity plot, what are the best sort of edges, right, of this, like the start and end of the similarity plot, which gives you the start and end of the retrieve moment. And then at ACL 2021 this year, we had a multilingual version of this, so as to sort of continue this not into just English, but other languages. And we are also continually trying to expand this to more languages. But the idea here was that we showed some multilingual models by using shared parameters as well as neighborhood language constraints. And we showed that these multilingual models that had information from two languages as opposed to one had smaller, like lesser number of parameters, but actually perform better than the unimodal models because of these shared parameters and neighborhood constraints. Then one of the other last tasks I'll talk about in this section is, like I said, after question answering and retrieval, this is a slightly different kind of reasoning or inference task where, given a current video and language premise, your job is to be able to predict what is a more likely next event. So in this case, if you look at this clip.
Oh yeah, oh maybe a shake.
Yeah, so this is basically a food blogger kind of video. This person is basically walking around in a market, and they are basically, the model will be given this video premise, right, and some dialogue happening in it. And its job is to predict out of these two events, which is the more likely one. And the right answer here is answer B, that the woman in the white shirt will pour the slush into the watermelon rind, which means the hollowed out the outer cover of the watermelon, as opposed to in a cup. So it's sort of like this subtle reasoning visually that since there are common sense, like in a common sense way, if this person is keeping hollowed out watermelon rinds in front of the machine, then they are going to use it to pour out almost use it as a utensil, as a container. And we also collected rationales for this task, so that again, the model is not maybe just trying to choose the right answer with shortcuts, but we can also create future tasks where the model has to also generate or choose the correct rationale among distractors. So another example is from more like a crime genre.
Got back to my apartment. That phone was on my doormat. It had a text on it.
So again, the idea here would be that if this is your current premise information, what would be the likely next event? Does this person take the phone and read the text, or hands it to the other person in front of him? And the idea is the first answer is correct because the rationale here, like you see on the screen, is that the detective will not probably hand a piece of evidence to a suspect sitting in front of him. So again, this is a very challenging task where the idea is to be able to predict what would be a more likely event. It's not looking into a long-term future, but more a next, like almost like event completion, but a little bit longer than that, right? It's not just a single action completion, but trying to understand sequences of events, but with a lot of background common sense knowledge needed too, in addition to the visual information. And one interesting thing we did here is that since we didn't want the data set to have very easy shortcuts, right? If the distractor answers or the wrong answers are very unlikely or things that are not definitely going to happen or totally unrelated, then obviously the models can perform much more easily and highly on it. So for that, to avoid that, we use this human and model in the loop adversarial data collection strategy called Hamlet, which is from a previous paper in collaboration with Facebook, which was called Adversarial NLI. So the idea here is that when you're collecting data, you ask annotators to give you more challenging examples that actually try to fool the current models. So basically, you take a state-of-the-art model. In this case, what we want is we don't want examples where basically just something like BERT or Roberta, a text-only state-of-the-art model, will just look at the information in the premise and be able to almost do language completion, right, to predict the next event. We don't want that to happen. We want to make sure that the data needs visual information to complete and find the next event. So you could feed that as the adversary in this Hamlet loop. So the annotators have to write distractors in a way that a state-of-the-art text-only model should not be able to find the right answer, right? So this is sort of human and model in the loop adversarial data collection example. And again, just two quick informations on the type of the data set we collected. So it had around 28 to 29,000 examples, around 10K TV show and YouTube blog videos. And also it covered, again, different genres from sitcom, medical, crime, travel, food, family, daily. And you can see that the good thing about covering these different genres is that the models have to start trying to understand very, very different families of actions, events, or verbs on the right side. And then in terms of initial models, we basically had a pretty sort of common kind of architecture these days where you would have a video feature encoder going into a transformer. And then on the text side, you would get a dialogue as well as one of the potential candidate future events. And then we also fed in some common sense knowledge graphs like Atomic from University of Washington's team. And so this is a pretty standard and useful common sense knowledge graph used these days. And then we would combine this information into a multimodal transformer, some of which we'll also talk about in the second part of the talk. So this would be the current sort of performance, right, where we showed ablations of each modality helping. The human performance upper limit is around 91%, and models currently are around 67% on this. And then there's been some good improvements with models like Merlot, which is a video and language pre-training model, also from University of Washington, using a lot of script knowledge, and it gets around, I think, 1%, so maybe around somewhere around 68 on this data set. So there's still a long way to go. And then lastly, the last example of video and language, I'll keep it a little bit short now because of the two sort of disconnections I had with Zoom. So just to come back on track, this would be a short slide where basically the idea here is that we are trying to create a data set that, given a textual query and a video, should be able to generate a highlight of the main events in the video that summarize this query. So if it's a shark is swimming underwater, but the video is showing a lot of things outside the water and around the city and so on, the model should be automatically able to detect the parts that show the shark. Or this one is maybe more complex. Glass is laying all over the street from broken windows beside other trash and debris in front of store buildings, right? So the green boxes are relevant to this query, then you skip the middle ones, then again, when it comes back to this view, then you have to choose those. But the more interesting part is that it's not just multiple moment retrieval, but you also have to understand the saliency among these moments. So which moments are more important if you had to create a shorter summary, or if you had to define like the importance ratio among different parts of the summary. So that's why it's more a saliency based highlight or summary task as opposed to uniform summaries. And so the data set sort of through 3 annotators shows you the green and bigger the bar, the more salient these 3 annotators considered this moment, as opposed to this one, only 1 annotator considered it more salient as opposed to the other 2, and so on. So basically, we collected 3-way annotations of saliency also across the multiple moments. So I'll not go into the models for this, but there's a moment detter style model based on detter and mdetter that you can see in the paper, and I'm also happy to discuss offline. So to conclude this part of the talk, we sort of combined all this information and different reasoning processes from our video and language benchmarks, and then we collaborated with other folks who have been working on video and language. So things like video and language translation, or video and language inference, or also how 200M QA and retrieval. So Microsoft, Santa Cruz, Santa Barbara. So we sort of came together and created this NeurIPS benchmark this year called Value. So it has around 11 to 12 data sets on video question answering, video retrieval, and video captioning, all of them also requiring language plus video understanding. And the goal was to be able to promote building unified multitask models as opposed to specialized architectures, such that you would have to jointly perform well on all these 11 or 12 tasks, even, for example, by sharing knowledge across the tasks for improving all of the individual tasks. Okay, so I'll finish maybe, I guess, should I just finish the rest of the talk, Animesh, and then maybe take questions?
Sure, I think you can.
Yeah, sure. Please go ahead. Let's do it that way.
Great. So yeah, so the second part of the talk will be about some kinds of these data sets that we've been looking at, right, as evaluation benchmarks. Now, the second part will shift a little bit of focus and start thinking about what kinds of models should we be using and developing to be able to tackle such tasks, right? So this part of the talk will focus on how to enhance these recent large-scale pre-trained language models that have achieved a lot of useful gains in a lot of NLP tasks, and how do we start making them more visually grounded and be able to handle cross-modal tasks, and also think about them for improving not just multimodal tasks, but also maybe language-only tasks or grounded robotic tasks and so on. And then also think about how to make them more unified, generalizable, and efficient. So it's obviously like a big several-year goal. I'll just give you a few examples of things that we've been looking at in this direction. So I'll start with something known as LexMERT. So this is around 2 or maybe 2.5 to 3 years ago, where given the success of large-scale pre-trained language models like BERT and Roberta and others, we basically build this sort of cross-modal version of BERT called LexMERT. And there were others also like Wilbert and so on. So the idea here was that if you look at the bottom part of the slide on the left corner, this is the usual masked language modeling task, right, that BERT uses, where you would basically create fill in the blanks, and then the model has to fill the blanks. So in this case, you would also have the top part on the vision side, where you could imagine doing something similar in the image based on objects and their relations. And you would basically, instead of having just the language encoder, you would also mask different kinds of region of interest or positional features and be able to predict them to learn an object relation encoder. And then finally, you would have a cross-modality encoder connecting these two things, which would then have pre-training objectives based on cross-modal tasks, right? So image and text matching, or basically being able to do cross-modal question answering, or even like cross-modal language modeling, right? So who, and then dash, eating, dash the carrot, and so on. So this was basically the goal of trying to extend BERT kind of masked language modeling ideas to cross-modal encoders. And back then, this was also a big jump into a lot of the multimodal tasks such as BQA and NLVR2 and so on. This is also an important task that is known as VisVis, where it shows a little bit of generalization capabilities, where these are images taken by people who might have visual disabilities. So the images might be out of focus or out of frame. Lexmert, for example, was able to get some good gains on images and questions about these images that are different from the usual distribution of VQA style datasets. Then I'll give a couple of examples on how did we extend this to video and language. So they were after Lexmert and Wilbert style image language pre-training models, there were some useful video language models like Hero, where again, you can imagine that if you go to videos, the mass language modeling kind of task just becomes something like being able to jumble the frames of a video and asking the model to unjumble them, or being able to mask or fill in the blanks inside different frames of a video, right? And then if you want to do it cross-modally, then you would, instead of having image text matching kind of cross-modal task, now you would have video and text matching kind of task. So one of the papers that we improved on things like Hero and video text matching pre-training models was known as December at NACL this year, where the two things we addressed was bringing in more regional information from the videos in form of dense captions that could give us a lot of more locally grounded information inside the pre-training network. And the other big problem that we addressed is that usually the ASR captions and the videos are very misaligned. So we had a new constrained attention loss, which would basically try to align the correct ASR caption with the correct frame timestamps of the videos. And the other example I can give, since we have limited time now, is something we called Clipboard. So the idea here was that it's more in the direction of efficiency or making these models more democratic. Because if you look at traditional video and language pre-training models, you will have to have offline video feature extraction as opposed to end-to-end training. But if you do want to also train the video features in addition to the cross-modal video and language understanding features, what we ended up doing for that is you can do some intelligent sampling where you don't use all the features of the video, but you only sample a few parts, a few clips of the video. And this is the general idea of how you can be able to also do end-to-end training of video and language models. So much more efficient models while still maintaining or even getting slightly better results than trying to do this for non-sampling approaches. And then I'll have just two small things as the last few slides. So when I was mentioning how to be able to unify these tasks, the goal was that if you look at the 200, 300 papers that you might find for different kinds of image and language tasks, right? So image captioning versus visual question answering or visual grounding and so on. You don't want to have specialized architectures for each of these different tasks. Ideally, you want to be able to have a unified architecture, which allows you to also share parameters, but also you also don't have to be thinking about how to tune and develop different types of architectures for those, right? So this was one of the first examples that we tried to do that unification. We called it BLT5, where the idea was to unify vision and language tasks by treating it as conditional multimodal text generation. And the idea here is that if you see my mouse pointer, you would basically treat each of these tasks as text generation. That's as simple as what I said, where if you look at the bottom side, you would have a prefix, which would be the name of the task. In this case, for example, visual grounding, which also you can think of it as referring expression comprehension. So given a phrase and an image, you have to find the box that contains that phrase, the information of that phrase. And then you would have the name of the task, you would have the text part of the task, and then you would have the visual part of the task. And then you would basically make the output be generated by an autoregressive text decoder. So for example, if you are doing something like multimodal language modeling or captioning, then the name of the task would be span prediction. This would be the textual part. Dash is dash over fire hydrant. And then this would be the visual input. And the output will have to generate man and jumping, right? These are the blanks that need to be filled. If you're doing something like visual question answering, then obviously the name of the task, like the prompt, would be VQA. Then the question would be the question, what is the man jumping over? And the answer would obviously be the answer. But in this case, it would be generated as opposed to discriminated over a vocabulary of answers. Visual grounding would be actually more interesting, where the task would be obviously the task prompt name, visual grounding. The input would be yellow fire hydrant. And then instead of detecting the bounding box, you would still actually generate the index or the ID of the box. So number 3 here, right, the yellow fire hydrant. And same for image text matching, it's true or false. So you give it the name of the task and then the text and the image, and then it has to say true or false, but again, as a generation. So this was the basic idea, and there were 2 big advantages here. So basically, if you're treating these as giving a task name prompt, and then the input of the text and the input of the image, and then generating everything, all the labels, all the answers, all the captions as text, it allows us to share parameters across the 7-8 different tasks, which were usually treated independently. And with 1/7 of the parameters, we were still able to achieve equal performance almost to the individually 7 times higher parameter tasks. And the other second advantage was that since you are making this generative, you can also handle rare or unseen answers. For example, in VQA, instead of being forced to have a vocabulary of only 1,000 or 10,000 answers and having the model discriminate and choose over them, you could also now generate answers that are not present in the discriminative vocabulary. So that would be basically the 2 goals here. Now, obviously, there's also been interesting follow-ups here where you could take the prompt idea and make it also 0-shot or few-shot, right, where you don't have to update the language model or the visual model. So this kind of direction has a lot of more future possibilities, and you can freeze different parts of this pipeline to be able to do 0-shot learning. And then again, the last example here would be the idea, like I said in the beginning, is that we've looked at cross-modal tasks, right? So we've looked at how to build things like LexMert, Wilbert, Hero for videos, right? Clipboard, and also unify them. But another interesting direction we've been thinking about as a community also would be how can we use these visual grounding information to actually see if we can improve language-only tasks, right? So can we actually take something like BERT, but instead of having masked language modeling as the only pre-training objective, right, where you have to fill in the blanks of the masks that you've created, maybe we can also have a pre-training function for each of the words to be able to find its visual mapping, right, in a visual world. So this was the basic idea of tokenization at EMNLP 2020, which was one of the first works to be able to try to take BERT and make it visually grounded. And it's as simple as I said, like basically an additional pre-training objective of BERT would be to now take the word and also predict its visual map. So there were 2 main challenges that cannot make this happen. One is that you basically train BERT on things like Wikipedia, whereas the visual mapping ground truth is for very different kinds of data sets like MS COCO, right? So the first step we did was you train a visual mapper on a multimodal data set like MS COCO, and then you run it on all of Wikipedia to get visual maps predicted for words in Wikipedia, because you also have longer sentences that BERT needs and much more data. And then since that's still not enough, because Wikipedia may not have very many visual words that are directly visually mappable, you do this in context, right? So you learn the visual mappings in context so that around other words around can learn the visual maps because of the surrounding information around them. So these were the 2 things that you would do to be able to get more visual maps for a lot of the words in documents like Wikipedia that BERT is traditionally trained on. And so here we showed how you can take language-only tasks like QNLI, MNLI, all the different kinds of glue tasks, and also some common sense tasks like SWAG, and improve over BERT-style models by using this visual mapping. And then we had a follow-up work called Widland KD at NeurIPS this year, where we also used distilled information from videos and showed that you can improve very specific tasks like PICA, which is physical common sense. So it needs physical knowledge, which is present in videos, or temporal knowledge in tasks like Tracy, and also glue diagnostic kind of data sets, where it showed that the video information mostly helps the knowledge or the external world knowledge component of glue diagnostics, and not things like logic or other parts of the task. Okay, so maybe I'll stop here. I'll skip the last part. This was an example of the opposite. So instead of allowing vision to help language tasks, what's a very simple cute example maybe of how does language modeling help a more grounded visual task. And just in 30 seconds, the idea here was, this is an ICRA robotics conference paper where given incomplete instructions like pour me some water in front of a visual environment with several objects on a table, this is an end-to-end example of starting from a microphone and a connect camera and be able to disambiguate these incomplete instructions using something like predicate argument parsing, filling in the different missing roles of this ambiguous or incomplete instruction by filling it with objects in the environment, for example, in front of the table. So if it's pour me some water, pour is basically the predicate, right? And theme is water. And then it has a location, initial source location and a destination. So you can start filling these with different environment objects in front of you and start creating sentences, right? So it could create something like pour me some water from the plate to the spoon, pour me some water from the glass to the cup, and so on. And then you could use a language model perplexity style idea to predict what is the most common way of filling this sentence given the visual objects around me. And then you would do motion planning to complete this. So I'll skip some of the demos that are available online. And I'll end with some concluding thoughts and next steps. So a lot of things to think about. For example, this is obviously just some of the beginning, right? So when we talk about videos, one of the still most challenging parts in video understanding is to be able to do long distance video understanding, right? So most of these data sets that we are looking at they used to be 10 to 20 seconds, right? Now, long videos mean maybe 60 seconds to 2 minutes because, I mean, to be fair, there's still a lot of information and actions and events happening in 2 minutes. But what about being able to understand things that span 30 minutes, 2 hours, a full movie, right? Multiple episodes of a TV show, for example, over relationships between humans or more multi-hop complex events, right? That you need to piece together to be able to get the answer. And then a very related question is continual learning of this information, right? So most of our current pre-trained models or other models are very static in that sense, that basically you would just have a static training data. But what if you have more information coming in, right? As if you have a deployed model, right? The video stream keeps continuously coming in. You can't just have a pre-trained model on the first half of your life and then expect it to work on the second half of your life, right? So how do we basically efficiently update these pre-trained models without having to retrain them from scratch in a very expensive and slow way every time? And this connects to other forms of efficiency, not just time and storage, memory, but also in terms of being able to not have to waste environmental resources, right? To always be able to update these every time, which has another connected question of whether unified universal models are better versus more specialized models, because if it's a unified universal model, which everyone's expected to use, then their efficient updating and continual learning becomes even more important. Yeah, I think I'll maybe stop here since I'm running out of time, but I think the other questions are already on the slide. Yeah, so feel free to reach out after the talk. Here's some of my contact information, and here's my group page and lab page, and we have PhD and postdoc openings. Thanks, everyone.
So thanks, Mohit, for that wonderful talk. So yeah, there are lots of questions I see. So let's see how many we can take. So there's a question from Shamok.
I guess I forgot to switch on my video also when I when my Zoom crashed. So sorry about that, but I'm here now.
So yeah, okay. So yeah, there is a question from Shamok, who is one of the organizers. Is there
I think Shomok can himself
yeah, I guess so.
take up the question. He's a panelist.
Sure, Mohit. Hi, again, a fantastic talk as always. So my question was, is there a specific reason other than empirical performance to fixate on transformers as a backbone while unifying these multiple modalities like vision, text, multiple languages, etc.? And do you think, of course, it's a bit of a kind of a subjective, I think, view as of now. Do you think would it be sufficient for, let's say, truly temporal reasoning, counterfactual, or even contrastive reasoning? What is your thoughts currently?
Yeah, I mean, I'm pretty sure. I mean, we are sort of temporally moving through models, right? So right now, transformers definitely have a lot of advantages. I'm sure there'll be some new things in the near future, but the advantage was obviously always that we don't need structural constraints maybe for different kinds of recurrence, right? And forcing the model to go through previous states, but now you have all kinds of self-attention to learn weighted combinations, right? Of all kinds of past and future information. So that was the advantage of transformers. But even currently today itself, right, there are alternatives that people are discussing. So for example, we have a new work on how to replace transformers in vision and language on maybe both vision and language side with things like MLPs, right? So there's been a lot of work on trying to replace transformers with simpler things like MLPs and other Fourier information, which could be much more efficient and simpler and faster. So we also tried recently on whether we can do this for both vision and language together for multimodal tasks. So I mean, there's one advantage or thought process, obviously, in terms of efficiency, because transformers will always be much bigger and slower, right, and more capacity and memory needed. But I think in terms of capturing temporal information, right, I mean, they do have that advantage, right, because they are inherently capturing multi-directional temporal information through self-attention.
Right. Anything about the counterfactual part? Sorry to.
Can you be a bit maybe more specific about which counterfactual part do you mean?
Counterfactual in the sense that any type of counterfactual reasoning over longer videos, right? So if you change something, let's say if you move Chandler from a scene, right? Or if you move the, say Chandler is putting a cup on the table, if you move the table, right? So something like that.
Yeah, that's a pretty interesting question. Yeah, I don't think it's definitely, I don't feel it's restricted to transformers, right? I mean, you could basically have contrastive learning also, again, in cheaper, more efficient ways. I mean, you could have more structured contrastive learning too, right? Where the model is first figuring out which part of the scene changed, right? And then trying to focus the reasoning on that. Yeah, so maybe it's more about better structured attention in this case, as opposed to like all self-attention. But I'll have to think more about that
Sure.
since that's something a little bit more specific. But thanks for the question.
Thank you.
I think you're mute.
Saptashi, you are muted.
Okay, sorry, thanks. Yeah, okay, so thanks for the nice discussion. So there are several questions. I'm not sure if we can take all of them, but let's take a few. So maybe
yeah, and also whatever we can't, I'll try to write
sure.
the answer.
So yeah, you can also see the question. So maybe
okay, yeah, let me see.
So in the Q&A section below.
Are the rationale predicted by the model? If so, how exact? Yeah, so in the VLEP VLEP task, right, which is the next event prediction, right now we only released the rationales as part of a richer data set. The current task does not need to predict the rationales. It's more about the premise of video and the dialogue, and you have to choose the best future event, which has been collected in this adversarial way. So you cannot have that many shortcuts, but the rationale can be used to create different kinds of tasks. I mean, obviously, the first thing you could do is just feed the rationale into the model to get much better accuracy, but that's sort of obvious. So we don't intend it to be used like that. But the more interesting usage is that can we have a task where the model doesn't just need to choose A versus B, but actually explain its answer, right? Explain its choice. So it could either be based on rationale selection or more interestingly, like rationale generation. So yeah, so there could be different tasks created out of the rationales. And then it seems yeah, maybe the questions have become a little bit out of context because I don't really know which part they're talking about. So maybe we can ask someone to ask the question, like, and then maybe we can move on, and I can type the answers after that. Or if you understand the context of some of these questions, I'm happy to hear from you. Maybe the last one seems pretty self-complete, right? So you mentioned intersection of continual learning and VQA. How would the evaluation look like? What kind of setting would be that for VQA? And if you could refer, Yeah, so this is a pretty brand new sort of topic, right? Because we've done some work maybe 2 years ago on continual learning, where if you're trying to do architecture learning, right? How do you update and learn the architecture in a way that you are basically continuously given different tasks? Like we took, I think, 3 or 4 different domains or categories of video captioning, and we said, how do we update the model architecture in a way that it avoids catastrophic forgetting, which means that it should maintain its performance on the previous video captioning domains and datasets, while also achieving the best it can on the new video captioning domains that are coming in. So you could imagine setting up the VQA task also in a similar way. Suppose you have 4 or 5 kinds of VQA subtasks, right? And you could set it up in a continual way, and the measurement would be that the model should not catastrophically lose performance or forget previous tasks while still. So yeah, it would be sort of an average performance. And then also the other thing would be efficiency measurements, right? So the evaluation would also be an efficiency, like what's the best approach that can achieve this, like avoid this catastrophic forgetting without having to retrain, or like while having to retrain as few parameters as possible. So those I think would be the 2 main goals here, right? Maintaining accuracy of old and new tasks, but also doing it in a most efficient way.
Okay, thanks, Mohit. So I think, yeah, about the other questions, if you can understand the context, and if you might just type the answer. But yeah, I agree with you that some of the questions may be a bit out of context at present, because yeah. Okay, great. Thanks a lot again for that wonderful talk and the QA. So yeah, so I think we would now move on to the next talk. Thanks a lot again, Mohit.
Thanks, everyone.
Thanks. Okay, so yeah, so the next talk is by Professor Raymond Mooney, and I see him already. Hello, yeah. So I'll introduce him briefly, and then the talk can start. So Raymond J. Mooney is a professor in the Department of Computer Science at the University of Texas at Austin. He received his PhD in 1988 from UIUC. He is an author of over 180 published research papers, primarily in the areas of machine learning and natural language processing. He was the president of the International Machine Learning Society from 2008 to 2011. He is a fellow of AAAI, SEM, and SEL, and the recipient of the Classic Paper Award from AAAI 19 and Best Paper Awards from AAAI 96, KDD 2004, ICML 2005, and SEL 2007. So today he is going to talk about deep learning for automating software documentation maintenance. So welcome, and it's a great pleasure to have you here.
Okay. Can you hear me okay?
Yes, we can hear you.
Okay, well, let me try to share my screen. Can you see that okay?
Yes.
Yes.
Does that look good?
Yeah.
Yes, all fine.
And it's
Good to
switching
go.
okay?
Yes.
Yeah.
Okay.
So over to you.
Okay. Okay, great. I think we're ready then. So I appreciate the invitation, and I'm glad to be here. Yeah, so I'd like to talk about some of our recent work on deep learning for automating software documentation. And this joint work primarily with my PhD student, Sheena Panthaplakal, but also some other colleagues of mine here at the University of Texas at Austin, Pengyu, Milos, and Jesse. So I picked this partly because of the theme of AI for data and data for AI. I thought this work was maybe a little bit relevant to that topic. And the idea is there's been a fair bit of recent work on trying to treat open source software repositories as an interesting source of data, and trying to apply machine learning to that to try to productively help the development of software by training on large bodies of open source software like you can get from GitHub. And learning all sorts of interesting things about software by mining that publicly available open source code. And people have tried applying a variety of statistical and neural language modeling techniques to code to support a variety of tasks, such as auto code completion, where you can figure out what you're going to type for the rest of your program, programming by voice, where you just want to talk about your program and get it. And then by using the language model to sort of know what normal code looks like, that something might be abnormal and might actually be a bug, is actually to use these large language models trained on open source software to do bug detection and repair. What I've been particularly interested in is trying to use open source software to learn a connection between code and natural language by mining large repositories of open source software that have both natural language commentary and code. And there's a variety of tasks you can look at in that context. One is language to code, where you learn, like for semantic parsing, to be able to map natural language directly into executable software. The other is to flip it around or do code to language, where you learn to generate natural language that's descriptive of code, to like generate comments automatically. Or a task I'll particularly talk about today is updating comments to account for code changes. And then code retrieval. How do we actually retrieve code using natural language queries? And by learning models that connect language and code from large bodies of open source software, I think you can learn to support all of these tasks. So initially, my work in this space was in the language to code space. I've actually been working on this problem of learning semantic parsers that map natural language sentences to formal executable representations, such as database queries. I've literally been working on that for decades, starting back in 1996 up until maybe a decade ago, when I sort of got out of that area. And I've always defined semantic parsing as machine translation from human language to computer language. When I was on sabbatical at Microsoft Research 7 years ago now, I worked with Chris Quirk on this problem directly of language to code, where we tried to map natural language descriptions to these scripts that were available on a site called If This Then That, or IFTTT. And we tried to mine the data on that site to automatically learn to map natural language to small little sort of script for your smart devices. These are a couple of my favorite examples from that. Flash my Philips Hue light bulbs red and blue when the Cubs hit a home run. Or this other one, remind me to drink water if I've been at a bar for more than 2 hours. So we tried to take that language and map it to actual executable code by training on data that was available on this IFTTT site. Just one last thing in this space of language to code is this idea of dialogue for language to code. Due to ambiguities and people not being precise about what they really want in their initial specification, it might be hard to map language to code in a single shot. And we might want to go engage in a back and forth clarification dialogue where, I initially say what I want, and then the system says, well, what about this case, and resolve this ambiguity and get clarification and go back and forth until it eventually has enough information to write the code that you want. And we applied this to this If This Then That site. And here's a sample little dialogue. And that was a paper back at IJCNLP back in 2017. So I've historically worked a lot on language to code, but more recently that I want to talk about today is our work on going the other direction of code to language. In particular, doing code to language for automating comment maintenance. So we had a paper at ACL last year on learning to update natural language comments based on code changes that I'd like to talk a little bit about. And then earlier this year at AAAI, we had a paper on a related problem of what we call just-in-time inconsistency detection between comments and code. And that's at AAAI this last year. So if you're interested, you can get more details in those two papers. The idea is that code is constantly evolving and changing. And a lot of times people change their code and forget to update their comments. And that can lead to all sorts of confusion and bugs. So in this case, you have an example here. We have some get score method, and say someone replaces the max in this expression here with a min, but they forget to update the comment that they should now change this highest to lowest. That can cause all sorts of confusion. So we wanted to look at this problem of how can we use all the data on open source repositories to train a model that can learn to update your comments when you change your code. So the idea is, maybe here we have this piece of code and we've added this to map this angle here into degrees. We want to know that, we need to change the comment to add in degrees to the comment. So the idea is that we start with some old piece of code and an old comment that describes it. we get a new updated version of the code, and we want to predict the new updated comment from that to maintain consistency. And so we particularly propose approaching this with an edit model. Rather than trying to generate the new comment completely, we just want to learn sort of a sequence of edit commands that will change the old comment into the new comment to properly get it to coincide with the new code. So when developers edit comments, they don't delete the old comment and write a whole new one from scratch. They just go in and slightly edit the old comment to update it to do the changes that adapt to the code. And we're trying to do the same thing. So we want to take, you learn to edit the old comment into the new comment rather than to just generate the new comment from scratch. We want to implicitly learn those edits by directly generating the new comment. If we tried to just generate the new comment using the old comment as context, we could just build a model that just takes the old comment in and the old code and the new code and just generates the new comment from scratch. You'd have to learn to copy a lot from the old comment in order to do that. We'd rather define actually an edit sequence where it learns to explicitly know what edit changes to make. And we believe that's a better way to learn to automatically change the comment to update it to be consistent with the code. So we have this example here where we replaced the max with a min, and we need to learn what we need to do is we need to edit this highest comment word to change it to the lowest comment word. So we want to address that with an edit model where we learn sort of a sequence of edit commands, and we put together a particular edit command sequence, but you could imagine various right. But this is just replace the old word highest with the new word lowest is the sort of edit sequence we want to predict to update that comment. And what we're going to give it as input is an edit sequence that encodes the changes that happen to the code. So with that, we replace this max with a min. So we get an edit sequence that defines what happened to the change in the code, and we want to predict an edit sequence about how we should edit the comment to update it appropriately. So the details of the model we use to do this are in the paper. We tried also transformer type models, but we actually found we got better results on this with a more older fashioned RNN model, particularly a bidirectional gated recurrent unit, a bi-GRU sort of model. So we take the edit sequence for the code, and we put that through a bi-GRU encoder, and we take the old comment and encode it using a bi-GRU, and then we give both of those embeddings to a decoder that learns to decode an edit sequence about how the comment should be edited to update it to be consistent with the new version of the code. And we found that, well, that just looks at things sort of locally. So we found it a little bit useful to do a beam search and generate multiple possible edits, and then generate the actual final edited code, and then re-rank the final edited code based on a re-ranking function that I'll talk briefly about. So the overall architecture uses, some RNN technology to encode the edit sequence from the code and the original comment, and tries to predict and edit multiple edit sequences for the comments, and then searches through a sequence of those using beam search to get several options, and then re-rank the final options to get the final best one. And particularly to give the final re-ranker some global information, we wanted to incorporate 3 pieces of information. We want to accurately update the old comment with minimal modifications. And to do that, we just, in the re-ranker, we use a metric that just looks at meteor, a classic MT metric that looks at, well, how similar is the old comment to the new comment? Because we don't want to change the comment unnecessarily. So being closer to the old comment, given everything else, would be better. But we also want the comment to be suitable for the new method and conform to whether their comment styles are appropriate for the project. So we also just build a generation model using a similar sort of RNN generation approach, seek-to-seek sort of approach, to generate the new comment just given the new version of the code. And we look at how likely that code that's generated from the edit sequence is given that model. And we do a final re-ranking that takes into account the beam score here is the original score from the original model, and then it takes into account the similarity to the old comment, and also how likely would you just generate that comment to be consistent with that new version of the code. And we set these hyperparameters based on validation data and re-rank to get a final best final candidate for the new version of the comment. Okay, so we ran a bunch of experiments on data that we mined from GitHub. So how we did this was we looked at a bunch of projects on GitHub. I guess the list here like 526 different projects on GitHub. And we looked at the sequence of commit histories. And we tried to find a sequence of 2 commits where both the comment and the code were changed from one commit to the next, so that we can learn a model of how to change a comment when you change the code from that data. So you're mining simultaneous updates to the comment code methods from consecutive commits. And here where it gives some little bit of data on that we collected, like 5,700 some training examples from 500 some projects. And then we also tested on completely separate projects as a sort of a cross project to show generalization across project. We tested on a completely different set of 281 projects from which we mined 736 examples of comment update. Okay, so we compared our edit model to a couple of baselines. One that actually can work surprisingly well, because a lot of times when you're changing the code a little bit, you don't really need to update the comment that much. You can actually do pretty well by just copying the old comment. So it just says, let the new comment be the old comment. Or you can just say, let me generate a new comment from scratch from the new method using a standard seek-to-seek RNN sort of generation model. But we also applied the same sort of beam search and re-ranking that we applied to our model to be fair on that. And then we also found that a lot of times they're pretty simple changes, like people will just change the output type. And also sometimes they'll add this thing where it's like, if the input is null, then output is null. So we came up with sort of just a hand-based template that actually works surprisingly well, as you'll see, but it's sort of a rule-based, sort of manually constructed baseline. And then we evaluated the new comments for the test cases in several ways. One is exact match. Did it produce something that exactly matched the new comment that the developers of the original code did when they changed the code in that way? A couple of other just generic generation metrics from MT that you can use to compare the old comment to the new comment to the gold standard comment from the data. And also a couple of metrics that have been developed that specifically look at edits that show how well you're doing at editing one string into another string. Despite being trained on more data, the generation model that just tries to generate the comment from scratch is doing actually quite poorly. So you clearly want to exploit the existing comment and learn to update it. Even the simple dumb rule-based model does significantly better than the generating from scratch model. But our edit model does the best, particularly if you look at these edit metrics. It shows how well it's actually editing the new comment into the old comment into the new comment. So these, I think, are automated metrics that sort of show that the model is learning to update the comment reasonably well. But I really think there's no substitution in a task like this for actual human evaluation. These automated metrics have all sorts of issues with them. So we did a smaller scale, but I think a pretty rigorous human evaluation, where we gave a bunch of subjects, and to do human eval in this space, you need to find experts. So we had 10 participants with at least 2 years of Java experience. All our code, I think I mentioned, was, if I didn't, we all do Java code from GitHub on this. And we give them up to 3 suggestions. One is the generation model from scratch. One is this rule-based baseline, and the other one is our edit model. But we also give them the option of selecting none. So we should have showed them, hey, here's the old code and the new code. Here's the old comment. So we show the human software engineer all those things, and we say, pick amongst these options, what is the best updated comment? But they can also select none if they think all of them are bad, or that the old comment really doesn't even need to be updated. We had each participant annotate about 50 examples. Each example was by 2 annotators, so we could look at cross-annotator agreement. And so here's some of the results. First, I'll just mention this Krippendorf alpha. We did get pretty good agreement between the two judges. So this is something that a reasonable software engineer can judge, is which one is a better updated comment. And the generation from scratch model does pretty poorly. The rule-based model a little bit better, and our edit model does the best. But there are a lot of cases where the software engineer is actually picking that none of those updated comments are really the best. And a lot of those cases are actually a case where the comment really didn't need to be updated, even though the data we collected was all collected under the restriction that the comment and the code were both updated. But sometimes people just make polishing changes to the comment, even though it doesn't really change the semantics to match the change in the code. So that led us to the next part of the project, which is all that data we collected assumed that when you updated the code, you needed to change the comment. But a lot of times when you update code, you don't actually need to change the comment. It doesn't affect the comment. So we had to look at this problem of code comment inconsistency. And this is a problem that other people have looked at in the past, is can we just learn a model that learns whether a particular comment is consistent with the code? And one way to do this is just to do what we call ad hoc tests, which is I just look at comment and code and see if they're consistent. But we also try to do this in what we call just-in-time comment code inconsistency detection, where we check when someone changes the code, does that change to the code require a change in the current comment? So this post hoc inconsistency detection is just, I'm given comment with code and I want to say, is it inconsistent or not? So in this case, it's getting that says the highest value, but it's actually getting the min. So we would say that comment is not consistent with the code, versus over here where it says highest and it's doing the max, that is consistent. But what we really want to do is do this in a real-time sort of just-in-time setting where we just saw the person change that max to a min. Now we want to know, does that make the comment that we had before about highest value consistent or not with the data? And so we want to check when the change is made to the code, does that render it inconsistent with the comment? And that's what we call just-in-time inconsistency detection. So the idea is, we have comment and we have code. So the post hoc approach is I give comment, I give code, are they consistent? But the just-in-time is, I just changed the code from min to max here. Does that now render the comment inconsistent? So just in time, when they make the change to the code, I recognize that I've now created an inconsistency between the comment and the code. So we tried to build a deep learning system that learns when you change code, does that render the code inconsistent with the comment? So we take the existing comment and encode that with a GRU, a bidirectional GRU. And we do some self-attention over that, so it starts to look a little bit more like a transformer. And then we also encode the changes to the code, and the details of this are in the paper, but we tried several ways of encoding the code changes. One is just looking at the sequence and using a biGRU. The other is there's been a variety of work in the area of applying deep learning to code that tries to use the syntactic structure of code by looking at the AST, the abstract syntax tree for the code. But we also developed a model that looks at how the AST was edited, sort of the change to the tree structure of the syntax of the code to see if that was better. And we used a gated recurrent neural network, a graph gated neural, so that's the GGNN is graph, I think graph gated neural network to do that. And then it does cross attention between the code and the comment, and then puts it through a couple of continuous fully connected layers to make a prediction. Oh, did that change to the code render that comment inconsistent with the code? And we try to train a model to learn when changes to code renders that code inconsistent with the current comment. So again, we went into GitHub and collected a variety of data for training this model, where we look at a commit history where both the comment is changed and maybe the code is changed. The code is changed, but maybe the comment is changed or not. In the case where the comment has changed, then we say, well, if the person changed the comment when they updated the code, then that probably meant that the existing comment was inconsistent. Now that can be a little bit noisy because, like I said, a lot of times people will change the comment where they'll just like maybe clean up a typo in the comment that they happen to notice when they change the code, but it actually wasn't the case that change rendered that old comment semantically inconsistent. So there's a little bit of noise in this data, and I'll mention that we did some cleanup on that later. But if they change the code and they didn't change the comment, so the new comment is the same as the old comment, then that's sort of an indication that the comment was already consistent with the code. Again, that could be mistaken too, because our whole point of using this technology is sometimes people are stupid and they don't update their comment when they should. But we're assuming that that's negative. So this can be some noisy data, but it is at least a reasonable set of data to train a model to detect comment code inconsistency when it's created when someone changes the code. So there's a little bit of statistics on the data set we created. We mined a pretty big data set of 800 and some projects and got some 32,000 training examples, and then we have like not quite 4,000 in the test case. And we look at particular types of comments for Java programs, at return comments, parameter comments, what we call summary comments, which is like the first sentence in the block comment before a method. But like I said, some of this data is pretty noisy because assuming this means this is consistent and this means it's inconsistent are not necessarily always true. So we created what we call a cleaned up data set where we manually looked at it and made sure that the consistent and inconsistent labels were correct for a small sample of 300 examples. And then the results show are the results on the cleaned up test data, and then the normal test data that might be a little bit noisy because of the assumptions we're making about how people are updating their comments in code. So there was a prior piece of work that tried to do just-in-time comment code inconsistency detection that was not using deep learning, that used a random forest approach with a bunch of engineered features. So they didn't actually use any actual use of the comment language or the code. They engineered some features. And so this is a baseline. Their system does reasonably well on our data set. In fact, it does better than just trying to do post hoc using a sequence model where you try to detect, is this code inconsistent with comment without taking into account the changes to the comment, to the code versus the old comment. But our edit approach does a little bit better. Our just-in-time, sequence-based deep learning approach. But we also looked at using the syntax graph of the code changes, as I said, using the abstract syntax tree. And then also this hybrid combines both the graph representation, the syntax tree representations with the sequence representation, and that does a little bit better on that, where that wasn't statistically significant. But this manually engineered approach did use some pretty interesting manually constructed features. And so we also added some of our own manually constructed features to these sequence and graph representations and boosted the performance a little bit more. So at the end, we're getting up to in the high 80s, at least on the cleaned up data, and in the low 80s on the not clean data that might have noise in it. Okay, so incorporating these existing manually constructed features gave us the best performance overall. Okay, so our paper at AAAI earlier this year then shows results on combining these two, because the idea is to use this in practice. Then you'd first you'd see a change to the code. You'd first have to run our consistency detector to check whether that change in the code renders it inconsistent with the current comment. And if you decide that that change does render the existing comment inconsistent, then you want to go ahead and generate a new updated comment. And the paper, we show combining these two processes together to do both consistency detection, and if it's inconsistent, then do the update, and then do both automated and human eval for that case. You can see the paper for the details on that. Okay, so I want to leave plenty of time for questions, so I'll try to wrap up here and spend a little bit of time here talking about future work. So maybe I wasn't completely clear that the existing work that I've presented here is all on method comments, where the comments describing the method, sometimes the return comments, sometimes the parameter comments, and sometimes just the block comments for the method. But it'd be interesting to look at other types of commenting codes, like comments at the level of an entire class, or inline comments. We just look at method level comments. We don't look at higher level, class level comments, or sort of immediate inline comments. Also, all of the results I've presented today are in Java. Of course, it'd be good to test these sorts of comment update and consistency detection methods on other programming languages. Another thing we've thought about and started to do some work on, and the results were a little bit disappointing, we're trying to use this thing only looks at the current method and tries to decide all these things. But maybe if I looked at an abstraction of that method in a higher level abstract class in the object-oriented hierarchy, that could provide me some interesting context. Or what if I looked at the methods that called this method, or the methods that this method calls? So we're calling that either the class abstraction hierarchy or the calling hierarchy. How could we add more context to understand this method better by understanding where it lies in the calling hierarchy and the class abstraction hierarchy, and use that information to improve comment generation and comment update? Then, of course, it would be nice to take all of these and actually put them into an interactive development environment where people, as they're changing their code, it maybe pops up this little window. Oh, I just noticed you changed your code. You might want to change the comment in this way, and then give them a nice tool for like accepting that change to the comment or editing it. So actually integrate these tools into an actual software development environment, and then do an actual user study, where we allow users to use these tools and see if that leads to them actually developing more effective software where the comments and the documentation is better maintained by using these deep learned tools that have been trained on all this available open source software. So I've assumed that when we find a comment code inconsistency, that means that, oh, the comment needs to be updated. But maybe it means that actually there's a bug in the code. So maybe comment code inconsistency doesn't mean that the comment is wrong. Maybe it means that the code is wrong. And how can we use this ability to detect comment code inconsistency to maybe detect bugs and decide that, ooh, maybe this is a problem with the code and not a problem with the comment. Another idea that we've talked about is this all tries to either generate the comment from the existing comment in the method or, generate it from scratch. But what about, a lot of times I might find code somewhere else in some other repository, and then take the comment from there and try to learn to edit it. So maybe I can find a similar method somewhere in some software library somewhere, look at the comment for it, and then just learn to update the generated comment for this new method based on editing a comment for a similar method in some repository somewhere. So I can use this edit model to actually learn to generate comments by retrieving comments for other previously developed code that's similar and edited it to adapt it to the current code. And the thing we've been looking at most recently that we have some initial results on that I don't have time to talk about is there's been a lot of work on language encode, but not with dialogue. So we've been looking at GitHub issues. I don't know how many are familiar with that, where they're actually discussions between developers about the open source software, maybe like a bug fix, somebody reports a bug, and then the developers engage in this dialogue on this GitHub issues tool to debate what the problem is and how to fix it. And we've been analyzing these dialogues and trying to learn a model that can learn to suggest like bug fixes based on the discussion between the developers. So you sort of have a bot that sort of contributes to the software development dialogue, say about a bug report, by having trained on all these other dialogues about all these other software issues that have been out there on GitHub. So it trains on a bunch of GitHub issue data to try to learn an agent that can engage in an intelligent dialogue about software. Okay, so I'll wrap up there to leave plenty of time for question, even given the fact that we started a little bit late. So I think deep learning applied to software repositories offers many opportunities to develop tools for improving software development, particularly in learning to connect natural language to code. In particular, we've developed these sort of just-in-time methods that every time you make a change to your code, it figures out whether that change to the code renders it inconsistent with the existing comment. And if it does, can suggest an updated comment that will restore consistency and train a nice deep learning model to do this based on all this available nice data that's now out there on open source software. And we've gathered some, I think, reasonable extensive experimental results on a reasonably sized corpus based on Java code from GitHub that tries to demonstrate that these deep learning techniques really can learn to do these sorts of documentation maintenance tasks reasonably well. Okay, I'll stop there.
So thanks. Hello. Yeah, thanks for the wonderful talk. Yeah, so I do see a couple of questions. You can see a Q&A window below. Maybe if you can click on it, you can read them also, or I can read them out also.
Yeah, so a slightly bigger question is,
no,
is there any
specific... okay, that's the chat. Can you see the Q&A, which is kind of beside it?
Oh, sorry. Oh, okay. Yeah, I got it. Is it highly dependent on modification on made? For example, max was changed to min, then the system should have the definition of max and min. But if the definition of the change is not clear. Function call A0 was changed to B0. Well, I mean, it would have to learn, you know, from the, I mean, it does use the language in the names of the functions. And so it would have to, you know, maybe it is a system, a user-defined function. But, you know, if that user-defined function has some reasonable English name to it, it could still exploit that. So we do what's usually, people do this, they usually what's called sub-tokenization, which is you break like names of methods and variables based on case, or based on the camel case or the snake case into individual tokens. And hopefully those are actually English words that the model of the code could learn. So it doesn't, and even min and max, it has to learn that from the code, what min and max mean, and that min means whatever lowest and max means highest. So as long as it could break apart the name of the user-defined function into meaningful terms that it can maybe relate to the English words in the comment, it could still hopefully learn to do that even for non-system calls, if I'm understanding the question. Does that answer? I guess. So that they don't have access to the speech, right? Okay. Hopefully that's okay. Your take on Codex. Okay, so yeah, so you know, Codex is of course made a big splash out of OpenAI in terms of they process on a lot of different codes. So you know, so they train on both the language and the code, and in some sense can complete on both. But I mean, it'd be interesting to apply that directly to this model for updating comments. But I mean, it's not specifically designed to do these specific tasks that I outlined. It'd more have to be where it was starting from scratch, like the start from scratch model. So it's really not going to be able to use the sort of existing content and the sort of edit capability that our model does. So I agree that, you know, when we did this work, that was actually before Codex came out, but it would be interesting to apply it to our data. But I think it's going to end up more in the space of the generate from scratch model, because it's not really learning an edit model of any sort, which I really think is a powerful tool in these cases of updating comments. How does the model behave as code gets more complex or larger in size? I mean, I guess we trained on a lot of real projects from GitHub. I think that's an interesting question. We could have looked at when it's making mistakes. I mean, maybe it's like for longer methods or something. We could have looked at how its errors correlate with certain properties of the code that it's maybe I think I don't have any quantitative data on this. This is where it'd be better to have Sheena here because she has more experience with the actual data. But I think not surprisingly, I think she did tell me that when there are a lot of changes to the code, that's when it has problems, right? That when there are just a few changes to the code, it's pretty good at finding the few changes to the comment to update that. But if there are huge amounts of changes to the code, not surprisingly, the system starts to fall apart. So I'm pretty sure that, yeah, certainly the bigger the changes are to the code, of course, the more complex the change might need to be to the comment. And of course, in those cases, the model is not doing as well. Okay, so that's all I'm
saying. I had just one small query. So just continuing on the point that you said, like if the changes are really big, then do you think it makes more sense to generate a comment from scratch?
That's a very good point, and I absolutely agree. So maybe at some point you need to learn that the edit model is not appropriate, that this code has changed so much that I would be better off generating the comment from scratch rather than trying to edit the old comment. So that's a very good point, and I think you would want to learn a model then to then predict when you should flip and say, ooh, this is just too many changes to the code. Maybe it's just as simple as the number of code token changes or something. It'd be interesting to check, but maybe it's just a simple threshold on the number of code token changes, which should switch you from an edit model to a generate from scratch model. But that's a very good point. It'd be interesting to look at that. Thanks.
Okay, so one of the organizers, Animesh, has a question. So yeah, Animesh.
Hi, Ray. Animesh here. So I was wondering, like when you were showing this generation of the comments, like Are you also thinking in future to incorporate ideas like explainability, because that might like resolve to some extent the problem that many of the software engineers were finding, that no code, no comment changes at all required. So if the model could be made a bit more explainable as to why the model is feeling that some comment needs to be changed or some new comment needs to be generated, that might that could probably help. So what would be your take on that?
Yeah, no, that's a very good question. I have actually worked on explainable AI. I was involved in the DARPA explainable AI project, but you're catching me between projects, because I've done explainable AI more on grounded language, more the sort of stuff that Mohit, my friend Mohit, talked about, where VQA. We've actually done a lot of explainability work on VQA. I've not done explainability for this code work, which I think would be very interesting. I think what you would want to collect in that case, which would be hard, is human rationales, because you need some data to train a rationale model. And so you would need, and that's not, you can't just scrape that from GitHub, right? You would have to actually ask software engineers, okay, why did this code change require this change to the comment? If you could get that sort of data, I think you could train a rationale model that could learn to, you know, provide those sort of rationales. The problem would be, where the hell would you get that training data? Because that's, with all the data we've gotten so far, we just naturally scrape from what's out there on GitHub. But that, people don't provide rationales for their changes when they make these changes on GitHub. Well, you could go look at the commit message. Maybe the commit message might provide some additional information on that. So it'd be interesting to see to what extent. Commit messages are sort of notoriously bad, though. People do not do a good job. If people put in really detailed rationales about why they made the changes they did in the commit message, then maybe, but I wouldn't be hopeful that that sort of rationales are available even in commit messages. But in general, I like that idea.
Yeah, so I think like we had a parallel project where we were doing the same thing with hate speech, but there it was a bit easier to get the rationals, because you could, you could resort on AMT workers to do it. But I think in this case, like it might be too much to rely on AMT workers to have these rationals tagged. I'm not sure, like, but like say first year or second year programming students, like if they are given code snippets and the comment messages, like it might be worth checking, like whether that kind of an annotation framework makes sense or not. Thank you.
Yeah, so I like, there's another question that did come up in the QA. It says, could a machine learning model be used to detect a region of code so complex that it needs a comment? So there is someone, I don't have the site for this, but there is someone who looked at when should I put an inline comment somewhere. Actually, it was Charles Sutton. Charles Sutton, if anyone knows him, he's done a lot of work in this language and code space and just machine learning for code. But he looked at this problem of learning when you should put an inline comment, that this particular line of code is sort of opaque and you really should add an inline comment. I think that's a really cool task of where should I put inline comments? So there, I know Charles Sutton has a paper on this for the person who asked that. But it's another really interesting problem in the whole comment and code space. Like I said, I mentioned inline comments in my future work session. There hasn't been a lot of work on inline comments.
Great. Yeah, thanks for answering all the questions.
Okay, well, thank you for the invitation.
Thanks again for that wonderful talk. So yeah, I mean, we'll now move on to the next speaker. Thanks again. Okay, so the next speaker, Chris, is he online?
I'm here. Yep.
Okay. Yeah. Hi. So yeah. So thanks a lot for joining, and it's a pleasure to have you here. Let me just introduce you briefly, then you can maybe start the talk, right?
Sure.
So Christopher Potts is a professor and chair of linguistics and professor of the computer science at Stanford, and a faculty member in the Stanford NLP group and the Stanford AI Lab. His group uses computational methods to explore topics in emotion expression, context-dependent language use, systematicity and compositionality, and model interpretability. This research combines methods from linguistics, cognitive psychology, and computer science, in the service of both scientific discovery and technological development. So Chris is going to speak on a very important topic, which is important for all of us: benchmark datasets, the essential resources on which all NLP depends. So over to you.
Thank you very much. I'm delighted to be here with you all. This is a really exciting event, and I just love the emphasis on data. As you can see, these issues are really central to my thinking these days. Just before I begin, I'll mention that I stashed a link to this talk at my personal homepage. I've got a lot of references to a lot of really interesting papers by lots of people. And if you want the full details on those, you'll find them at the end of the slide deck. Yeah, so my title is The Essential Resources on Which All NLP Depends. And you can probably hear that that's a play on a famous quotation from the oceanographer and explorer Jacques Cousteau, who said, "Water and air, the two essential fluids on which all life depends." And my comparison here is, of course, that in NLP, and in fact, throughout all of artificial intelligence, data sets are the essential resource on which all of our progress depends. So I find that an inspiring idea. Now, I should mention that Cousteau's quotation actually continues. He said, "Water and air have become global garbage cans." And some of you out there might be pessimistic enough that you want to extend my comparison into that very negative space. I'm more of an optimist. I think we've learned lots of interesting and exciting stuff about how to build benchmark data sets in our field. So I'm not going to go so far as to say they've become this polluted, but they are of such central importance that I think we should have in mind that things could get bad very quickly if we're not attentive to what our benchmark data sets really contain. Because after all, we are asking a lot of these data sets in NLP, and as I said, throughout artificial intelligence. Just think about the many roles that they're supposed to play. We use them to optimize models. We use them to evaluate models, to compare models, to enable new capabilities in models, to measure field-wide progress, and also for just basic scientific inquiry. This is pretty much the entire game here. So if we're not using reliable, interesting, important benchmark data sets to drive all of these questions, we're really deluding ourselves to think that we have solid results and have made progress. And that just reinforces the notion that benchmark data sets are absolutely essential. We live in good times for benchmark data sets, I feel. If you've been in the field for a few decades, you can think back to a time when we had very few data sets. And I'm reminded in this context of a quotation from Aravind Joshi, another explorer. This time we'll use analogies from the cosmos. Aravind said that data sets are like the telescopes of our field. And he actually worried at the time, which is about 2007, that we were behaving like astronomers who wanted to see the cosmos, but refused to build any telescopes. And I think he would be pleased at the state of the field today when we have more benchmark data sets than ever before. And that's giving us a chance to see what benchmarks are like when they exist in this field and in an era of really rapid progress. And that's an important thing about benchmarks that we should all have in mind, that they saturate faster than ever before. And what I mean by saturate is that we develop systems that surpass our estimates of human performance for those benchmarks faster than we ever have before. And let me give you a sense for this. So what I've got on this graph here is on the x-axis from the year about the 90s through to the year 2020. And on the y-axis, I have a normalized measure of distance from our human estimate of human performance, which is this red line here. So the first data set I'll highlight is MNIST. This is a famous data set. It was launched in the early 90s, and it took about 2 decades for that data set to be saturated, for us to see superhuman performance from a model. The switchboard data set is a similar story. It first appeared in the 1990s. And for the speech-to-text task, it took about 2 decades for us to have systems that were superhuman in this very rarefied sense that I'm using that term. The ImageNet dataset was launched in about 2009, and it took about 10 years for it to be saturated in this sense. And now what you're going to see is that progress is going to pick up really fast. So the Squad dataset came out in about 2016. It was saturated in about 3 years. Then we had Squad 2.0. It was saturated in even less time. Then the GLUE benchmark came out. GLUE continues to be important. And if you think back to the original paper, the authors actually say that they expect that this benchmark is so ambitious that it will take a long time before models do really well on it, when in fact it took about a year for us to see systems that were superhuman in this narrow sense. SuperGLUE was, of course, launched as an alternative to that. And it was supposed to be harder, but it again took only about a year for us to see systems that were superhuman in this very narrow sense. Now, I think it's perfectly reasonable to be a little bit cynical about what it means to be superhuman in the narrow sense that I'm using that term. I think that's entirely reasonable, but we should remind ourselves that these results would have looked like science fiction 20 years ago. We are talking about tasks, about benchmarks that many systems of even 10 years ago would have been unable to enter, to say nothing of achieving such astoundingly good scores. So maybe they're not superhuman, but this is certainly one measure of progress. The flip side of this, of course, is that when benchmarks appear now, we find limitations in them much more quickly than we ever did before. And to give you a sense for that, I'll just offer you a few comparisons across different data sets, starting with the famous Penn tree bank. It appeared in 1993. It continues to be used to this day. And this timeline here with these red dots are identifying papers throughout that time period that identified errors in the Penn tree bank. And you can see that there are relatively few of them. They all come from a few groups. This is really important work of finding errors, and you might have a suspicion that if more effort had been placed on finding these errors, we would have found even more of them. Now let's fast forward a little bit to the Stanford Natural Language Inference Corpus. It appeared in 2015, and right away, you have an outpouring of papers identifying shortcomings in that data set. And it's not just errors in this case, it's also things like artifacts that derive from the data set creation process, and also instances of really problematic, pernicious social biases, in addition to errors, of course. Squad appeared 1 year later, and again, you get a bunch of papers, in this case, talking about artifacts and related shortcomings right away. It's very different from the kind of easy life that the Penn tree bank got to lead for a very long time. One more point of comparison, this one is kind of interesting. I mentioned ImageNet before. It appeared in 2009. And for a while, it got to lead a kind of quiet life as a standard sort of benchmark like the BTB there. But then, of course, the times are changing, where we've reached a really introspective moment when it comes to thinking about data. And so in more recent years, you get, again, an outpouring of papers identifying different kinds of shortcomings in that data set, not just errors, but also things related to artifacts and social biases. And this seems kind of inevitable as we think more about benchmarks and we're more ambitious in creating them, we're also going to find their limitations more quickly. So here are my central questions for today. There's a lot we could think about when we think about developing reliable benchmarks for the field. I've picked just a sample of them, and if anything, that might just inspire you to think about additional issues we can discuss. Here's my quick rundown. First question, should we be relying on naturalistic data, or should we be relying on crowdsourcing, which would be more controlled? Now, my answer here is that we should use both. I think there is value in both kinds of methods, and so we should be making use of both of them when we think about developing new benchmarks. What about adversarial examples? Should we collect data sets that we know are really hard for our models, or should we be looking to benchmarks that contain more of what you might call the common or average case? I've been a proponent of developing adversarial data sets in the past, so I certainly think there's value there, but not exclusively. Again, my answer is going to be both. Both of these things clearly have real value for us. What about synthetic data sets versus naturalistic ones? Now here, I think almost everyone in the field believes that naturalistic benchmarks have an important role to play. So what I'll be arguing actually is that also synthetic data sets could play a role, an important analytic role, and so there's a place for them as well. I hope you're not worrying that I'm being very wishy-washy here and giving all these both answers. This is really just about embracing all of the exciting new methods that we have. Maybe there'll be some twists here. Let's look at another one. Should we be doing human tasks for our benchmarks or what I'll call machine tasks? And here you might think, certainly we should be doing only human tasks because that's the really important thing that we're all striving for. But again, in what I hope is a little bit of a twist, I want to say that there's going to be value in both kinds of methods here. Final question. Leaderboards, we're all driven by them. They control our lives as professionals. Are they good or are they bad? Here, I hope you're kind of thinking that I'm going to say they're purely bad, but no, actually my twist is that I think that they have both good and bad aspects. And so there you can see it's just about figuring out how to weight those two kinds of opposing things when we think about the roles that leaderboards should play. So that's a quick rundown, and let me now dive into each one of these in a little bit more detail. Starting with this question, should we be relying on naturalistic data or relying mainly on crowdsourcing, which would be more experiment and laboratory driven? And the fundamental reason that I give a both answer here is that I think this is really about trade-offs. I think both of these things have important things to contribute. What I mean by a naturalistic data set would be something that you found and maybe curated. So you could scrape something from the web with all its metadata, or just use a found database or something like that, something that was not collected primarily for developing NLP models. On the plus side, I think this data is likely to be abundant, pretty inexpensive to collect, and also genuine in the sense that it was created for some other purpose beyond just helping us in the field. And those are certainly positives. But we could balance that against some clear negatives. So the data will likely be uncontrolled in ways that you don't fully understand. It's likely to be limited to things that are naturally occurring, which could really limit the kind of analytic questions that you could pose. And of course, we might worry that because it's found and curated, it's also intrusive and maybe not privacy preserving in the way that we would like. Contrast that with crowdsourced data set. This would be like something lab grown where you have people do controlled tasks. Here, it's going to be very controlled in terms of the data set. It's going to be privacy preserving because we can opt in participants and even let them opt out. And it's also likely to be very expressive because, of course, you could have people do very unusual things as part of your crowdsourcing task that really provide you with something like exactly the information that you're looking for. There are clear negatives as well. Of course, it's likely to be scarce and very expensive to collect. And it also might have a contrived aspect, which might go hand in hand with it being very expressive. Your task might be very unusual and not naturalistic in ways that we really value. But there's good and bad in both of these things. And what I'd like to highlight is this trade-off between being genuine and being expressive. And the question would be, can we develop methods to create benchmarks that will have both aspects, that will leverage the good from both sides of this? And I think we can. And let me give you one example from a recent project that I've been involved with, which is called the DynaSent project. And that stands for dynamic sentiment. And you'll see why it's dynamic, because we imagine that it's going to have multiple rounds over the course of its lifetime. For DynaSent, we start with what we call Model 0, and this is a big sentiment model that we train on lots of existing sentiment benchmarks. Model 0 is primarily a device for us for finding challenging, naturally occurring sentences in the Yelp academic data set. So this is going to be naturalistic, found and curated data. And what we do there is a simple heuristic, which is we say if the model predicted positive, but the example occurred in a negative review and vice versa, it's probably a difficult case and one that we would specially value. That's just a heuristic. We then run that through a human validation pipeline, and that gives us our round one data set. The round one data set is now used as a kind of engine to develop a second model, which is another big model that we train on a lot of existing sentiment benchmarks combined with our round one data. And now what we do with Model 1 is use it as a device in a crowdsourcing experiment where we have people interact with Model 1 and try to fool it. And in this case, we're using crowdsourcing methods to create new examples that we know will be difficult for this very good Model 1 that we developed. And an important thing about that, which I want to linger over in a moment, is that we actually prompted these crowd workers with existing naturalistic sentences and had them edit them. And we think that that increased the naturalistic flavor of the examples that were lab grown as part of round 2. That's fed through the same human validation pipeline, and that gives us the second round of our data. And I've given over here in the corner of the screen some details on the splits. There's a lot of different ways you can think about DynaSent. And I think that those play off the fact that rounds 1 and round 2 are different in this important sense, with round 1 being more naturalistic and round 2 being more controlled in the sense that we're having these crowd workers try to fool a very good model as part of creating the data set. And I really want to emphasize that the prompt thing helped us a lot for round 2, where we're having people write original sentences from scratch. We found that when we gave them these prompts, they used them and they made minor edits by and large to create their new example that fooled the model they were interacting with. It also led to examples that had more, that were longer on average and had a greater vocabulary on average than the condition where we didn't give people these prompt sentences. And really what I think we've done here by giving them naturalistic prompts is free them from the very difficult burden of having to do creative writing as part of one of these crowdsourcing efforts. Instead, what they had to do is taking an existing naturalistic example and modify it to get the job done. And that led to some really exciting examples that I think we would not have seen in real quantity if we had just been using the round one method of harvesting these examples. For example, just to pick one kind of systematic pattern we see, people hit upon the strategy that if they shifted perspective in their example, they could pretty easily fool the model. And that led to a lot of examples like, my sister hated the food, but she's massively wrong. Or maybe more facetiously, breakfast is really good if you're trying to feed it to dogs. I love these examples. I'm sure they're out there in the wild for us to find, but the crowdsourcing effort really gave them to us in a lot of density, and I think that's very exciting. Let me move to my second topic now, which is the question of whether we should be using adversarial examples or just relying on kind of average case examples to build up these benchmarks. And you can see that I'm in favor of adversarial examples. That was part of the DynaScent project. But there are voices out there saying that we should really be focused on the most common cases when developing benchmarks, and the adversarial ones might lead us astray. Again, though, I'm giving a both answer. I think there's value to both of these things. Just to sketch this out a little bit, let's just say that the standard approach is one where you create a data set from a single model independent process and you divide it into train, dev, test. The adversarial case, which was introduced a few years ago and has been really exciting in terms of marking progress, is subtly different. Here you have a separate test set that's created in ways that you suspect or know will be challenging given the system you've developed and the data that it was trained on, maybe in the standard way. That's adversarial assessment. And then we also have now, thanks to the DynaBench platform, full adversarial data sets. These are data sets where the train, dev, and test were all guided in some sense by attempts to fool a model or set of models that we think are top performing. So this is the landscape here, and I think all of these things have been really fruitful. I should mention here that I'm using the word adversary, but that might be too strong. I think there are a number of flavors of adversaries that might be useful to think about. We could have the simple inquirer who just poses systematically a bunch of examples as part of an assessment to try to figure out whether a model has acquired a certain target capability, like it knows about antonyms or something like that. We could also have the challenger, and this would be where, based on something that you know about the training data, you're pretty sure that you have examples that are going to fool models that were trained on that data. The frenemy would be someone who is really truly adversarial. This could be like the crowd workers that I mentioned from DynaSet. They're trying to fool the model, but they're doing it for the goal of developing better systems as we work with their examples and train systems on that basis. And then you could contrast that with a true adversary. This could be someone, a kind of black hat hacker who is actively trying to concoct examples, not even close to naturalistic, that we know will fool top performing models in ways that could lead a deployed system to perform very badly, for example. All of these, I think, have their role as well. The DynaBench platform was part of the engine for round 2 in our DynaScent project, and it's led to lots of interesting data sets. This is an open source platform that makes it very easy for us to run tasks where crowd workers interact with a model to try to fool it. Here's a rundown of the DynaBench-based data sets that I know about, and I think more are about to hit the market soon. And the result of this is that we've learned a lot about the dynamics of these adversarial data set projects, and I think that's leading to stronger models. And I'll try to summarize that evidence in a second. I do want to mention, though, so I'm coming down on the side of saying that both of these approaches have their value, and we should be making use of both of them. I think there is a counterpoint there in a recent paper by Sam Bowman and Dahl, where they kind of say that adversarial data set collection maybe is not the way to go, and we should focus on the average case. And here are 2 important quotes from the paper. First, they just say that adversarial examples are not a panacea. Adversarial filtering can systematically eliminate coverage of linguistic phenomena or skills that are needed for the task but already well solved by the adversary model. This mode seeking, as opposed to mass covering behavior by adversarial filtering, if left unchecked, tends to reduce dataset diversity and thus make validity harder to achieve. I think they're actually absolutely right in this quotation here, but what you can hear in this is that we should be pleading with them to make use of both methods, because I think adversarial examples have their place, but I wouldn't rely on them completely, because I agree that we want examples that will kind of coverage the average case, the mass covering that they're referring to here. But that's not to say that we don't want to push on these models to make sure that they can cover the long tail of very intricate and difficult things that are rare in the world, but that humans make sense of very easily, and therefore our models should as well. There's another quotation from the paper that I want to highlight here, which is that they seem to be saying that standard evaluations are sufficient for the kind of broader goals that they've set for benchmark dataset creation. This position paper argues that concerns about standard benchmarks that motivate methods like adversarial filtering are justified, but that they can and should be addressed directly, and that it's possible and reasonable to do so in the context of static IID evaluation. That's like a push for the standard approach that I mentioned before. And here again, I would just say, first, we don't have to be filtering. Our data sets could consist of examples that are adversarial and those that are not with respect to some class of models. And I just really want to emphasize that there's value in having both kinds of examples in the data sets that we create. And just to make that vivid for you, just think on the job to be done here for these benchmark data sets. We want, of course, that the models we create with them can handle the average case, like for sentiment, the food was good. But we also need these models to handle those very difficult cases that our crowdsourcing effort uncovered for Dynasend, examples that are rare in the world, but very intuitive for people to make sense of. That's the complete job to be done. And you can see why I'm pushing for a both answer to this question, because the average case benchmarks might handle case zero, and we might need the adversarial methods to really get good coverage on things that are like 1 through 3 and all the other kind of things that are out there that we don't fully know about, but that could surface as part of adversarial dynamics in a benchmark data set creation effort. That's another one with an interesting neologism. So here are the major lessons that I think we've learned so far from developing data sets that employ both of these methods. First, it's just true that top systems have often found unsystematic solutions, despite maybe even being superhuman according to our metrics. And that's something that adversarial assessments have shown us really clearly. However, and this is really important here as well, progress on these challenge sets seems to correlate with meaningful progress in the field. For example, for natural language inference, many of the challenge sets were launched before the BERT models came on the scene. And those challenge problems looked really difficult for the models of the day. And now you can find that simple fine-tuning of a model like BERT solves those challenge data sets. And that seems like a real mark of progress, that these larger models that many of us are working with are actually able to accommodate the long tail of very difficult cases as well as the average case ones, right? This is important. Present day systems can get traction on these adversarial cases without degradation on the general case. If this weren't true, if performing well on the adversarial examples was always at the expense of the average case, it would be worrisome. But since it's very clear that these systems can do both, again, that gives me a both answer to the overarching question of which methods we should be using. And finally, and this is really important here, even if you set aside developing better systems, the role for adversarial examples could be just helping you prevent a really embarrassing thing from happening in the world, which is that you deploy a system and people find simple cases, intuitive cases where it fails, and those cases define public perception for your system. It seems to me like it's just smart to use some measure of adversarial assessment to prevent that very negative outcome. All right, my third question here, should we be using synthetic benchmarks or naturalistic benchmarks? And as I said before, I think everyone agrees that there's an important role for naturalistic benchmarks throughout AI. And so what I really want to do here is argue that there could also be a place for synthetic data when we think about the stock of benchmarks that we're all relying on. And here's the central piece for that for me. When we work with naturalistic data sets, it's really important to keep in mind that probably both the data set and the model that you're exploring are unknowns or partially known in the experimental sense, right? Think about the standard recipe. You have some naturalistic data set, and you have very partial understanding of what that data set contains because it's a huge sea of examples you harvested or examples you crowdsourced. Using that data set, you're going to now train a model. And maybe the point of doing these experiments is that you don't fully understand what that model is capable of or how it works. So you put these two unknowns together and you get some output, something happens, maybe a mistake is made. And the question is, where do I assign blame for the mistake? Does the problem lie with the model or with the data set? Now, given that both of them are unknowns, it might be very difficult for you to offer a confident answer to that question. But if the data set is partially synthetic, you can probably fully understand what it contains, and now the mistake is either easily traced to the data set or something that you might explore as a shortcoming of your model. And again, let me make this vivid with a little bit of a story here. So especially for natural language inference, we have a very intuitive set of learning targets that come from kind of logical semantics. And one of them is just this intuitive learning target that if sentence A entails sentence B, then not B entails not A. This is the famous reversal of entailments that comes with classical negation. So let's imagine that's our learning target, and many people have set it as an important learning target. And we have this observation that top performing NLI models often fail to achieve this learning target in the sense that models trained on the big benchmark data sets have not learned this fact about negation. A tempting conclusion here would be to say that those top performing models, for whatever reason, are incapable of learning negation, using this observation, this set of observations, as evidence for that claim about models. However, importantly, we now know that those benchmarks severely underrepresent negation. And so as soon as you say that, you realize that the observation we made about failing to achieve this learning target might not be a problem with the model. It might just be a fact about the data set, which might not even fully and unambiguously specify what the learning target for negation might be. And I actually think that that's precisely what has happened with this particular case. So to address this question, in my group, we developed what we call the monotonicity NLI data set. And I've called it a slightly synthetic data set for reasons that I'll make clear here. So for the positive part of the data set, we started with an SNLI hypothesis, like the food was served. And then we, as analysts, looked up using a resource like WordNet, a more specific form of food like pizza. And we used that to create this slightly synthetic example, pizza was served. Having done that and assuming the soundness of WordNet in this case, we can now fire off two examples, A neutral B and B entailment A. And then importantly, we have a second half of this data set called negative MoNLI. The only difference here is that now we start with negated premises from SNLI, perform that same WordNet substitution, and now we apply the monotonicity rule and we get two examples, but now with the entailment pattern reversed. A entails B, and B is neutral with respect to A. We use this first as a challenge data set with a little bit of fine tuning. And here's the full story here. So we have a few models, so two pre-BERT models and one BERT model. They have their various forms of pre-training, and they were all trained on the SNLI benchmark. And let's focus in on that BERT row there. So BERT does really well on SNLI at about 91. It does extremely well on the positive part of our data set, suggesting that it knows something really interesting about those lexical relationships. But for the negative part of our data set, it plummets to 2.2. It's very clear here that what the model has learned to do is simply ignore all the negations in our negated examples. And so you might think, oh, this is really despairing because BERT has just failed to acquire any information about negation. However, with only a very modest amount of fine tuning on our negative examples, and with very careful splits to make sure that the model is still being asked to generalize in very challenging ways, we now can boost the performance of that same BERT model to 90 on the negated examples without really any degradation in performance on SNLI itself or on the positive part of our data set. So the overall lesson here is that it was a failure of SNLI, not the models, that led to the models being unable to handle negation. And as soon as we solve that data coverage problem, those models perform really well on our learning target, right? And here's the bottom line. This was all possible because of the slightly synthetic data set that we created. And what we've learned here is that when we turn back to a naturalistic benchmark, we do so now knowing two things. First, BERT can in principle learn negation. Just gave you a kind of existence proof of that. And we also know that data coverage will be a major factor in whether or not that learning target is realized. On to my fourth question. this is a little bit trickier, but I still want to give a both answer to this. Should we be relying on machine tasks like simple classification things, or should our benchmarks move to the kind of more open-ended interactional things that we find from actual human life and human interactions with language? And again, what I want to say is there's value in both of these things, maybe for the long term. But there is a kind of thing that I worry about a lot with the way we pose these benchmark tasks, and the way, in particular, the way we estimate human performance on those tasks, which is in a very kind of machine-oriented way. Just to give you a sense for how vexing this could be if, say, you were a crowd worker, let's think about the NLI labeling case. So imagine that you're a crowd worker and you're given this pair of sentences. The premise is a dog jumping, and the hypothesis is a dog wearing a sweater. You might say, okay, that's clear. I read the guidelines. That's a neutral example. What about turtle contradicts linguist? You think, well, I can imagine a possible world in which there are turtles that are linguists, but I was told this was kind of about common sense reasoning, and no turtles in our world are linguists, so I'll give this the contradiction label. So far, so good. Okay, what about a photo of a racehorse and a photo of an athlete? Here you might really be wondering about whether or not any animal could be called an athlete, right? This is a kind of point of lexical uncertainty, and it seems like there's no simple fact of the matter. And if we were humans interacting about this question, we would certainly have some kind of discussion about whether or not animals can be athletes. But here you're a crowd worker, and so you just got to guess. And so maybe you say entailment, and somebody else guesses differently, and we register that as some point of uncertainty. But in the end, we're going to infer a single label for this, and that label might obscure this important point of variation that I just identified. Here's another example: a chef using a barbecue and a person using a machine. You say, okay, I'll buy that every chef has to be a person, but is a barbecue a machine? It really depends on what kind of job you've posed and what you mean by these terms. Again, let's discuss and debate. But what we actually do with these crowd workers is force them to make a single label choice, because we know that that's the kind of thing that our models need. But it's certainly not reflective of the human capacity to think about lexical ambiguity and uncertainty in the context of entailment, right? So this is the important thing. Humans would say, let's discuss. And now you can see that when we say human performance on some benchmark, we're actually talking about like average performance of harried crowd workers doing a machine task repeatedly with no chance for discussion and debate, that very human thing. So this is a point of real concern, I would say, and it might be distorting progress on this and other problems. A very common response here is to say, hey, let's leap all the way to the other end of the spectrum here. Let's just run Turing tests, right? Because a Turing test is a kind of very human thing. I mean, there were some concessions to the machines in this case, like they don't have to be embodied, they just have to have conversation. But beyond that, humans are really allowed to do anything, including, of course, discussion. So you might think, let's have our evaluations be more in that mode. The problem in particular with the Turing test is that humans are really not good participants in it, and they fail in both directions, right? So in the first Turing test, for example, one of the people was repeatedly misclassified as a machine in virtue of the fact that she knew a lot about Shakespeare. And so that's one kind of failure. Another kind of failure is that people are very susceptible to cheap tricks that lead them to believe that even very simple systems are human. And one of the more recent Turing tests with this AI, Eugene Gustman, is an example of that. And we don't actually have to go all the way to the Turing test to think about how these evaluations could go wrong. For example, you can find on the internet recordings of people interacting with Google's tool Duplex, and those people routinely fail the Turing test in the context of their interactions with this system. And even more down to earth, you could think about, for example, natural language generation and all these papers that are emerging that show that even crowd workers can't really tell whether a given sentence was generated by a big language model or a human. And that's a very narrow kind of failure of the Turing test, I would say. So we can't swing all the way in that direction, but surely there are some interesting points in between these two extremes, right? So we have these standard evaluations, like which really pose the question, can a system perform more accurately on a friendly task than a human performing that same machine task? This certainly has a role for our field because it's scalable and it's objective and it's easy to kind of have these questions posed field-wide and all of us to participate in answering the question for various systems that we're developing and questions we want to pose. So I think that has value, but it's not going to tell the whole story because it's not a very human thing to be doing. And again, we could leap all the way to the Turing test at the other end of the extreme, but there's so much interesting place in the middle here. For example, we could ask the question, can a system behave systematically, even if it's not accurate? This would be more like keying into human notions of systematicity and compositionality in the meaning sense. Can a system assess its own confidence, know when not to make a prediction? This is a really challenging task in metacognition that we could pose as a first order goal for the systems that we developed, reflecting its importance in human cognition. Or can a system make people happier and more productive, right? I'm kind of optimistic about this because nobody really needs to run a Turing test, but many people have questions like happier and more productive for systems that we deploy out in the world. And you can imagine a day where so many of those assessments are being run that they can actually become primary assessments and take some of the weight off of the standard mode that we're also locked into now, partly as a result of convenience. Final question here, leaderboards, are they good or bad? And I think a lot of us think that they have bad elements to them, but we continue to rely on them and think about them and participate in the leaderboard culture that we're all part of. And partly what I want to say to you is that that has many good aspects and you should not feel so ashamed. And what we should really be looking for is an opportunity to build better leaderboards that will engage deeper questions for us so that they can be even better than they currently are. But even in their present state, I think they can be a force for good. But let's start to balance the good and the bad here. Kind of the crux of it for me, the overarching issue is summarized in Strathern's law, which says when a measure becomes a target, it ceases to be a good measure. If we all get overly fixated on one benchmark or set of benchmarks, we will mistake progress on that benchmark for progress in some broader sense, and we might be deluding ourselves by making that kind of inference. So that's something to be worried about. But there's clearly good elements to this. And if you've participated in scientific fields outside of the hardest of hard sciences that don't have leaderboards, this might really resonate with you. Leaderboards provide an objective basis for comparisons, and in doing that, they create opportunities for wild-seeming ideas to get a hearing. If you have some very unusual idea about a model, and a priori people say that that seems like a bad idea, but you do well on a leaderboard, people might pay attention to you. And that really contrasts with fields that don't have leaderboards, where the only kind of assessment that you might get might be from peer reviewers. And if they're closed-minded about your contribution, that might be the beginning and the end of the conversation. So the leaderboard could clearly be a force for good in allowing wild ideas to get a hearing. But there's plenty of bad things here. And a lot of this has to do with the culture and the way we think about and talk about leaderboards as measuring tools. So some bad things are, first, we get conflation of benchmark improvements with progress, right? Whereas I think we all kind of know that doing epsilon better on glue does not necessarily mark progress. We should be aware also that even a large gain on glue might not correspond to anything like progress for the true goals that we have, right? Because we don't want to run afoul of Strathern's law here. You also get a common conflation of benchmarks with the empirical domains that they're part of, right? So you get newspaper headlines that say things like squad is solved, or sorry, the newspaper headline might say question answering is solved. And we all know that what that actually means is that some system performed better than our artificial measure of human performance on the squad data set. If we say question answering is solved as a shorthand for that much more articulated and narrow claim about the world, we're really kind of confusing ourselves and certainly confusing people outside of our field who might not be sensitive to all the nuances of the difference between a benchmark and the wider area that it's part of. And that relates to this third point here, which is that benchmark performance doesn't necessarily mean that you're doing better in terms of progress on the capabilities that we actually care about. We have to keep that in mind. And we should make sure that we don't talk about benchmark results in ways that would muddy the water around these issues.
Hello, Chris.
Yes, go ahead.
Yeah, sorry to interrupt. So we need to complete your talk in the next 3 or 4 minutes. So yeah.
Oh, I see. I started late, so I thought it would be okay.
Sure,
you
can take 5 more minutes, I guess. Sure.
Okay. Oh, 5 more minutes is fine?
Yeah, sure.
Okay, that's plenty. Yep. There's just one more thing I wanted to say about leaderboards, which is let's accept that they exist, the good and the bad, and think about how they could be better. And one thing that's really important here is that I think we should make our leaderboards more multidimensional so that they can be more tailored to the actual things that we want to measure in the world. There are a bunch of really exciting efforts out there to develop software systems that will actually help us meet those objectives. DynaBench, which I mentioned a few times, is one example. DawnBench and ExplainaBoard are also attempts to offer us leaderboards that could be tailored to specific goals that we have. And because I know it best, I'm going to talk about DynaBoard. I think this is very intuitive. Let me just give you one example of how we could have a dialogue around the leaderboard as opposed to just accepting it at face value. So what I have here is a bunch of results for question answering systems. Those are given along the rows here. And the way we're working is that we've allocated most of our scoring to performance. We really care about that F1, for example. But we also have a bunch of other things that we're going to measure: throughput, memory, fairness, and robustness. And I've given those all equal weight here because maybe I don't yet know how I want to weight them differentially. And that leads to a set of DynaScores that are over here on the right. And the DiBerna model looks best according to this particular weighting. And this might be a kind of null starting point. But now imagine that instead you're in a context where you really care about fairness more than throughput, memory, and robustness. So you boost the amount of value that you're going to give to that particular metric, also valuing performance above all else. Now an interesting thing has happened. Electra large is the better choice here, and the DiBerna model is in second place. And of course, you can imagine that as we think about and motivate different weightings for all of these different metrics, we might end up valuing very different models as a result. And I think that's exciting because it could mean that the metric is part of the overall proposal, and it might be very tailored to the particular goals that the analysts have or the people deploying the system have. So in summary here, just quickly for these leaderboards, at present, they tend to be one-dimensional, F1 and accuracy and things like that. And as a result, they're not sensitive to the context or the use case that's being addressed. And of course, we set the terms entirely as the research community. And that means that we built all of these things around machine tasks and not human tasks. But I think we're headed into an exciting world where leaderboards could be much more. They could be high dimensional and fluid. And they could be fluid in the sense that they could be sensitive to the use case and the context. And the terms of the metrics, like the DynaScore weighting, could be set by the stakeholders. And in turn, we could build them more around human tasks. We have the analytic techniques. There are going to be some culture changes necessary to achieve this, but I think it's possible and could lead to lots of exciting new notions of progress. All right, and let me wrap up here. I began with this observation that benchmarks are the essential resources on which all of our fields depend. And I posed these central questions and I gave motivated but wishy-washy answers to all of them. I think all of these methods have value and all of them should be used and allowed to interact with each other as we develop more and better benchmarks. And of course, just to plant some ideas in your head, of course, this is by far, far from being the only questions we could think about. We could also think about disclosures and the importance of them in understanding our benchmarks. We could also think about how we're going to achieve cross-linguistic coverage for benchmarks, given that now most of them are in English. We could think about statistical power, and of course, all of us are worried as dataset creators and model developers that our systems will embed pernicious social biases, and it's important to think about how we could get out of that trap. And I'm sure you can think of other issues that are important for us to think about as we go off and develop lots of exciting, new, reliable, interesting, challenging benchmarks. Thank you.
Thanks. Thanks, Chris, for that great talk. Yeah, I mean, that was a very informative talk, actually. So we have several questions. I mean, if you see, there is a Q&A button or icon below, you might see.
Sure. So should I just go through them?
Yeah, I mean, sure. I mean, I can read them out if you prefer, but maybe if you just go through them, that would be.
Sure. I'm sorry, I'm losing my voice a little bit. Let me just cough for a second. So the first question I see here is there any specific advantage to using Roberta instead of BERT? There may well be. I think for many tasks, Roberta has proven to be better. But there still are differences among these transformer-based models. And the question of advantages could actually be tied up with issues of efficiency, for example. So let me go back to my example here. You might be thinking about just raw performance, of course. But if you're thinking about things like memory and throughput and efficiency, then, for example, the larger models are going to perform less well than the smaller models, even though the larger models might be better on raw performance. And that's what I would encourage us to think about. Not whether in absolute terms one of these models is better or worse, but rather how they differ and how that might play into achieving the goals that we set for ourselves. Second question, in the specific case of sentiment analysis and perhaps NLU in general, can we say we could create adversarial data sets synthetically using a generative model that takes a vanilla sentence and emits variance by adding elements like adjectives, quantifiers, adverbs at the syntactic level, and more complex constructs like irony, sarcasm, puns, humor, emoticons, poetics, rhetorics at the pragmatic level? I love it. I think we should be thinking a lot about this because it could be very efficient and it could help us in a naturalistic way key into really challenging phenomena that we want our models to capture. The actual landscape of people trying this is a little bit rocky, with some of them proving too artificial and some of them actually working really well to develop better systems. So I think the answer is we should think about this because the winds are clear, but more innovation is needed to really realize the full potential of this approach. But I hope people pursue it. Third question, connecting with your comment on NLI models failing to solve negation examples. Does a model failing on an adversarial sample indicate lack of adversarial sample in data sets only, or do architectures have something to say there? Oh, I think architectures certainly matter. I can certainly, for example, imagine architectures that would fail to learn the monoticity property of negation that I mentioned. And so that might be a case where even though you give that model a synthetic benchmark that has an unambiguous learning target with lots of good coverage across examples, the model still fails. I think that's wonderful because then you could say, look, the data set supported it, the signal was there, but this model failed. And that's the kind of conclusion that we often want to reach because it's exciting to rule out a class of models. But the more worrisome thing is that we're actually misdiagnosing those failures as model failures when in fact it's a problem with the data. And synthetic benchmarks could help us clear up that question. So this is interesting. So question, for measuring human intelligence, we have IQ and others. For machine intelligence, we have the Turing test and maybe the Chinese room. So what's the future of benchmarks? So what I said about being multidimensional and being careful what you measure and all of that, that applies to humans as well, right? So human intelligence is highly multidimensional and any specific test will not measure all of those dimensions. And so we should be careful about saying that any one measure gives us everything we need as a way of ranking people or whatever. I hope we're not doing that. I hope we're recognizing the multifaceted nature of intelligence for humans. And then the exciting thing is to think about also pursuing that kind of multidimensional approach for models we develop. This is interesting. I didn't touch on this. Are there any data augmentation techniques that you can suggest for creating synthetic examples in order to create benchmark data sets? Yeah, augmentation is wonderful. This is kind of related to that earlier question. I do think we can think about augmenting in automatic ways or maybe quasi-automatic ways. That's kind of what we did with the MoNLI data set, where the augmentation was partly automatic and partly relied on us checking the examples and making small adjustments. And that gives you a really interesting benchmark really quickly. And I think that could be productive. And we should again be thinking about data augmentation as a way to achieve more robustness and maybe also to find and fix problems in the models that we're developing now. Absolutely.
Great. Thanks, Chris, for answering all those questions patiently. And yeah, again, it was an absolutely wonderful talk.
Oh, that's very kind of you. I'm sorry I'm losing my voice, but I'm really glad I had the chance to do this. Thank you for all for the questions and this chance to interact with you. It was great.
Thanks. It was our honor to have you here. Thanks. Thanks. Okay, so we will move on. So the next part is, I guess, the result announcement of the datathon and a felicitation. So I would leave this to Shamok and Sunaina. So Shamok, yeah, okay.
Yes. Yes.
Hello.
You can hear me, right?
Yeah, I can hear you. Yes.
Yeah. Okay. Yeah.
Okay, thanks.
Just a second.
And your screen is visible also. Yeah.
Sure.
Okay.
Okay. So welcome to the last part of today's session. Uh, uh, I am Somak Aditya, presently a faculty at CSE Kharagpur. On behalf of my fellow organizers, Vidisha, Jayesh, and Sandipan, it's my pleasure to kick off the first part of the Datathon Award ceremony. I'll first give a summary of what are the competitions, what are the tasks that we defined, and then ask Sunaina to present the awards to the winners. So the first task was the glucose NLI knowledge challenge. So I'm sure that you heard a lot about NLI in both Mohit's talk and for Chris Bott's talk. The original task was taken from Microsoft Research's glucose dataset, which is a code switch dataset. It was a natural language inference task where a premise is a conversation written in code mixed English and Hindi. Hypothesis is a human written fact about the conversation. For this datathon, we wanted to simplify a bit. The challenge was to determine if external knowledge is required to determine if hypothesis is entailed by or contradicts the premise. For example, you may not look at all the information. For example, on the right, you see a conversation asking for direction to a place called Basanpura. Imagine a particular location. So they are asking for a direction. Hypothesis asks for another place, which could be in the same direction or maybe unrelated geographically, right? You do definitely need external knowledge to solve this example. And I would also love for you to think about whether this is the chicken and egg problem, right? Whether we would, without an external knowledge, will such problems be solved at all? So we had a total of 2,240 examples. It's a small data set. We got it annotated by 3 independent annotators. It was an amazing effort by the lab members of Complex Network Research Group at IIT Kharagpur and putting in an almost 75 hours personnel hours effort. Additionally, I should also thank my fellow volunteer Pratik Joshi of CMU for putting in hours of effort on evaluating and setting this competition up in Kaggle. The second task is the Emmanuel Dataset Challenge. Here, we look into a specific question answering task, which is finding answers to questions related to smart TV. So the manual for this device is also provided. You'll have to find out the text in which in the manual where the answer to that question is. It's almost like a retrieval come question answering task. We had overall 700 such questions and 550 were provided to the participants for training their models. Again, it's a smaller data set. However, a larger corpus consisting of manuals of the devices are also provided for pre-training. So this kind of summarizes the 2 data sets today for which we are going to present the award. To present the award, it's my absolute pleasure to welcome Dr. Sunaina Sitaram, who is a senior researcher at Microsoft Research India. She, along with her esteemed collaborators, have organized many special sessions, workshops, and code switching in Interspeech 2017 to 20 and NACL 2021. Presently, she focuses on evaluating massive language models, multilingual speech, and NLP. Her goal is to make all the content in the world available to the people in the world, regardless of level of education, age, race, gender, or their abilities or skill sets. So I would hand it over to Sunaina. Kindly turn on the video And if you could say a bit about what was your motivation on the glucose data set, that would be fantastic.
Sure. Thank you so much, Somak. I hope you're all able to hear me. Thanks, first of all, for the invitation to come here. It's great to be part of the IndoML, in this way. And as far as glucose and NLI are concerned, as you are aware, right, natural language inferencing is one of the hardest tasks in NLP. And there are very few data sets and benchmarks available, and they cover very few languages. So when we were working on code switching and when we wanted to create this glucose benchmark, we thought that this was a gap which we wanted to address. And we thought, some of these multilingual models are doing reasonably well on other code mixing tasks, but maybe we'll get a better idea of whether they perform, whether they're really able to handle code switching or not if we create this NLI task, which is more challenging. So that was the motivation behind creating the NLI task and the glucose benchmark in general to measure how well these models are doing across a variety of tasks and also language pairs. So we are always interested in adding more tasks and more language pairs. So if anyone is interested in contributing, please get in touch with us. And we are very happy to see that, there are different conferences and workshops that are using this benchmark. And we really thank you for choosing the glucose NLI data set to work with in this challenge. So thank you to the organizers and also the participants for doing this. Yeah, that's what I wanted to say about the glucose NLI task.
Thank you so much, Sunaina, for the nice summarization of what you are doing. Glucose, which is a beautiful contribution, and thanks for the data set. Thanks for making the data set public for all of us.
Sure.
So the first set of winners in the glucose NLI challenge is both of these teams. This team are single-member teams, Naman Poddar and Vatsal Venkatakrishna. Can I please call Naman to switch on his video, and while Sunaina congratulates him on this.
So congrats to Naman Poddar, and you are the winner of the glucose NLI knowledge part of the datathon at IndoML 2021. So congratulations, thanks for participating, and all the best in your future endeavors.
The second team is again a single member team with Vatsal Venkatakrishna.
Congrats also to Vatsal Venkatakrishna. You are also jointly first in the glucose NLI knowledge competition of datathon at IndoML, and all the best for your future endeavors.
Yes, thank you, Dr. Sunaina.
Okay, great. The next one is winners of the e-manual challenge is a team brute force. With Tanya Singh, Pushpa Agarwal, Sakshi Agarwal, Raymond Chaudhary. If you are here, can you please turn on the video so that Sunaina can present the.
Congrats to all of you, to Team Brute Force, Tanya Singh, Khushbu Agarwal, Sakshi Agarwal, Raymond Chaudhary. You are the first prize winners of the e-manual competition.
Thank you, ma'am.
Thank you, ma'am. Thank you so much, ma'am.
Congratulations.
Thank you so much, ma'am.
Great to see an all-women team, and hope you continue to participate in lots of competitions, and all the best for your future.
Thank you, ma'am. Thank you so much, ma'am.
Okay, so I would also like to kind of, since we have a little bit of time, would you be able to say something from the team brute force? What was your experience in this competition? Anyone?
So team members can now switch on their cameras.
Yeah.
Yeah.
I can see Sakshi. Do you want to say something?
Yes, sir.
Yeah. Go ahead.
Thank you.
What was your experience like in the competition with the data
The experience was very great. It was very great to be a part of this competition, and thank you so much for inviting us to this facilitation ceremony. It motivated us a lot, and we felt very, very good to be a part of this hackathon, and it was great. Thank you.
Yes, sir.
Yes, it was an amazing experience, like exploring machine learning and AI as the first subject we encountered in this semester, and getting into the competition is really helpful, and we got to learn new things. It was really a great opportunity. Thank you.
Yes, sir. So we enjoyed like throughout the whole month. It was a very exciting and an enjoyable journey. Thank you so much for this opportunity.
So
Yes,
same
sir.
for
Thank you so much for this opportunity.
hi.
And we all
Great.
were newbies in this field, and we did very great. So it was a great motivation to be to start in this field.
Yes, sir.
Okay. Okay. So same for Naman and Vatsal. Naman, if you are here.
Hi. Hey. Yeah, it was a great fun to be the part of this competition. Like, yeah, I enjoyed it a lot. Yeah, this was my first second Kaggle competition. So yeah, it was fun to be the part of it.
Great. And Vatsal?
Yeah, likewise. Like Naman said, it was my first proper Kaggle competition, which was held at such a serious level too. And ranking so high in the leaderboard was really a good motivation to continue further in this field.
Okay. Okay. Thank you all for participating, and congratulations again for winning this very difficult competition. I can see from the F1 score of the winners is quite even now it's quite low. For example, the macro F1 score for NLI is 0.49, micro is 7.8 or something like that, and same for F1 score in Emmanuel is 6.9 or something. 69% or something, right? So it's quite difficult challenge. You can easily see that. And congratulations again. So yeah, the last one that I wanted to mention is the ongoing COVID-19 India dataset proposed by IBM quite recently, right? So they wanted to propose open-ended challenge, unlike the 4 that we have proposed, primarily driven by Mayank Agarwal and Tathagata Chakrabarti from IBM Cambridge. They will decide the top 3 participants who will win cash awards based on a set of esteemed panelists who will decide the award winners rather than a leaderboard. So if Tathagata or Mayank is here, Mayank Agarwal, could you? Okay, so I don't think they are there. If they are present in the next part of the award ceremony, I think Jayesh will call upon them. Okay, so here I think we would finish up our award ceremony part 1. Thank you again for the participation. Thanks to all volunteers. There has been a lot of volunteer effort. It has been a fantastic experience to work with Jayesh, Vidisha, and Sandipan, and many of the authors, actual authors from both the Blueproof research work and the Emmanuel research work, especially from the Synergy group and the Microsoft Research Lab. By here, I would hand it over to Saptarshi. Any last words for the session?
Okay, hello. Yeah. So, so what is the plan after this? That Shunayana presents? No,
we finished the session.
Okay, fine. Okay, thanks everyone for attending yet another very exciting session of IndoML. So we had 3 talks, as well as, again, I would also like to congratulate all the winners of the hackathons. Great.
And we
so
come back
yeah, so thanks again. We come back for the next session at 4 p.m. Indian Standard Time.
Yeah.
Thanks everyone. Thanks. Bye.